Good morning, everyone, and welcome back as we continue in the Environmental Bioethics course within the program of Bioethics, the Master of Science in Bioethics at St. Thomas University. In the name of the Father, the Son, and the Holy Spirit. Heavenly Father, we come before your presence in the name of your Son, Jesus, and we ask always to send your Holy Spirit to illumine our hearts and minds, to discern your will in our lives and live according to your will. We ask your guidance and inspiration as we deal with these bioethical issues in this course involving the environment, care for the environment, care for creation, as you have made us the one species that is steward of all the other living species on earth. We realize it's a great responsibility, and at the same time that you grant us the grace to be able to carry out this stewardship in a good way so that we may have a livable planet for many generations to come. As always, we ask for those who are in most need of your divine mercy, in the name of Christ our Lord. Amen. Father, Son, and Holy Spirit. So before we get into today's topic, which is going to be on energy, I want to ask, first of all, with regards to the stats course, all right, if there are any questions or comments, I have a couple of things also I want to contribute, one in particular, but we can just minimize this for now. Yes, so anything in particular that you want to ask or comment? You got some feedback already on the homework?
Yeah,
and on the test? Yes, okay. And how is it looking?
I think we did all good.
Okay, yeah. So far, everybody passing. All right, good. I'm glad. Okay, well, I have a little comment that I wanted to state, and I'm recording it so that the others will have the benefit of it, because last Tuesday I was able to join in the class finally, and hopefully this Tuesday I'll be here again, God willing. But I asked a particular question about the p-value last time, and what does that p-value represent, or the complementary, which is signified as alpha, right? The alpha 0.5, right? I'm sorry, 0.05, 0.05. Mm-hmm. What is that? And I wanted to get a clear answer, actually, on the concept, conceptually. But I didn't get it. However, it was not my class, so I didn't want to pursue it any further because it's Dr. Minea's lecture, of course. So I bring back that point. What is that alpha equals to 0.05? What does that mean conceptually? Yes, Emma?
I'm just here, just picturing like the curve. I don't know what it's called, is that a histogram?
Right. Normal distribution?
Yeah.
You're talking about a normal distribution, bell-shaped curve, right? Yes, okay. Mm-hmm.
And the 0.5 is towards the end, to the right, to the left.
Okay, first of all, it's 0.05, right? We have to, because 0.5 and 0.05 are two different numbers, right? What is 0.5 in percentage?
50%.
50%. So statistics deals a lot with percentage, right? Because it's a percentage that, that's what we call a probabilistic model. If we look at, I'm going to stay on the qualitative, on the conceptual. And this, by the way, I think, in my opinion, is a good complement between these two courses. That's why we keep in the stat course in the program, because pretty much the other 7 courses are very qualitative in the sense that I'm talking about a variety of topics, whether it's human life or environmental, many different topics, but you notice that I haven't presented too many statistics or numbers or quantities, more concept. For example, variation, when we talked about evolution, right? Variation within a species. The typical variation is normalized. In other words, there's a normal distribution most of us are average height, but then some people are going to be taller, some are going to be shorter, a few are going to be extremely tall, and a few are going to be extremely short, right? That establishes what we call a normal distribution, and many distributions in nature are normalized that way. They're standard bell-shaped curves, okay, which are also known as Gaussian curves. So the stat course quantifies it. It's all about the numbers, okay? So that's why it's a good complement. But still, the concepts are very important, and to see why we do stats, because it's a pain and it's a burden on the brain to be doing these stats. To what purpose? Well, because it is what we call a probabilistic model. We have two ways of looking at nature. Anything that is from our eyeballs out, you know, we intuitively process in two ways. One is deterministic and the other one is probabilistic, meaning that probabilistic is the chances of this happening. What are the chances of it being they right now, here? Well, it's 100%, right? So probabilistic gives us this average, gives us these numbers, these stats, the percentage of things, the percentage of probability of something happening or existing and so forth. However, excuse me, someone just chimed in. Just want to see what happened here. Oh, okay. Oh, I heard a bell.
Okay, I'm back.
Okay, no problem.
Thanks.
Sorry. And but the other model is deterministic. So probabilistic and deterministic. All right. Deterministic is the existential, real life, actual existence. In other words, that we actually exist right here and now as determined human beings. So we're not probabilities, but as a population and even as individuals, we belong to a probability, right? We belong to a group, to a number of individuals. It could be individual human beings, it could be individual living beings, et cetera, et cetera. So these two models forever are interacting and going back and forth, probabilistic model and deterministic model. And I use a lot the example of medicine because medicine is a probabilistic art, science, and also art, all right? Meaning that the doctor will never say it's 100% this illness. You have a 90% chance or a 50% chance or a 20% chance of recovery and so forth. But again, that percentage needs to be applied to each individual. So we have, let's say, a 90% chance of recovery from an illness. Are we in the 90% or are we in the 10%? No one can tell us that until it actually happens, right? And so probability is based on facts of the past projecting into the future. And what happens is that we are neither in the past nor in the future, we're in the present, which is a continuous present. It's an ongoing present. Okay, so it's kind of a philosophical existential issue, but the bottom line about statistics is that it tries to quantify this world in which we are immersed, but also has to do with chance. And chance is integrated to the actual process of evolution, which is very interesting. It was one of the insights of Einstein with his two theories of relativity, that those two theories of relativity, which explain the bulk of how the universe happened and is continuing to happen, is that integral to those two theories of relativity is chance. And we can translate that into the biological realm when we look at the process of evolution, specifically in mutation, right? Which is one of the four forces of evolution, but mutation is by chance. In other words, the chance that this particular cell on my skin will get cancer from UV exposure, it's a probability, all right? It's a chance occurrence, and it may or may not. So if I expose my skin unprotected to UV light, there is a high probability that I will get cancer. But for each particular deterministic cell in my skin, whether it gets cancer or not, that is left up to chance, all right, to a chance occurrence. So there's the element of unknown, if you will, built in to our existence and the existence of everything in the universe. All right. That, believe it or not, has to do with this p-value and the alpha of 0.05, which is what we call confidence level, all right? And there are basically three levels of confidence in science. And these are standards, but these standards are a convention. It's a convention that the scientific community, the bulk of the scientific community in the world has agreed to, like a convention. For example, a convention is the red light in traffic. The red light, society has convened that the red light means stop. It could have meant green, it could have meant go, you know, but we chose red for stopping because red, naturally intuitive in nature, red tends to be a color of alert. Typically, we seldom see red in nature, especially in animals. And when we see red in animals, it's because the animal typically is bleeding, all right, which is a dangerous situation. As opposed to green, which in nature, green is all over the place, and green is positive in the sense, typically, I'm gonna lower this a little bit. Typically that green represents that the plant is alive and it's flourishing and so forth. So it's a good, green is a good feeling thing. It's a systems go ahead, right? So it was natural to choose green as go in the traffic, but it could have been the opposite. It's a convention. There's nothing in my car that tells my car stop when there's a red light, right? I have to process that. All right.
Father?
Yes.
Sorry, my internet keeps going in and out. I'm back on, but I only see your blue window screen. I don't see the slides.
Right, because that's all I have. Your link to the desktop, and I'm talking about statistics. So I have not started the presentation yet.
Okay, thanks.
Sure, no problem. So I'm just talking about statistics, and I'm focusing on the p-value and the degrees of confidence, all right? So I'm asking the question that alpha equals to 0.05. What does that mean conceptually? Because I asked the question last Tuesday and I really didn't get an answer from anyone, but I didn't want to interrupt our lecture either, right? So I'm doing it now. That alpha equals 0.05 is the complement of a statistic, in other words, of a percentage. And what is the percentage? What is the complement percentage of that?
95.
95%, exactly, 95%, okay? So the complement of 0.05, if we translate 0.05 into a percentage, what percentage is 0.05?
5%.
5%, just like 0.5 is 50%, right? Okay, remember, easy things, I mean, easy conceptual things, and people get stuck on that. I can tell you, people get stuck on this all the time, converting fraction to decimal to percentage. But at this level, we should be very fluid in that, and it's a mental exercise. It's a mental exercise, okay? So 0.05 is equal to 5%, is equal to 5% in fraction. So 1/10 is 1/5. 1/05 is 1/20th. It's 1/20th, 1/20, right? So again, the mental exercise. And here's the mental exercise. A lot of people get stuck on this, and that's when they say, oh, I hate math, because they're not using those neurons, okay? And it takes ATPs. So how to translate 0.05 into fraction? into fraction. So the double is 0.010, right? The double of 0.05, 0.010, or 0.1. 0.1 is 10%. What is 10% in fraction? Is 1/10, right? 1 over 10. And then we go back, half of that is 1/20th. So it's 1/20th. Anyway, these mental exercises are good. Otherwise, if we don't use those pathways in the brain, we lose them. Okay. At any rate, 95% is the confidence level. And 95% is the basic standard for something to have significance in science. It is a standard. It is a convention that most scientists in the world have agreed. And this is relevant for lab experiments. If I get a result in the lab 95% of the time, all right, then that is the minimal standard for claiming significance, something significant, that the alternative hypothesis is significantly different from the null hypothesis. And therefore, I can reject the null hypothesis, all right? In other words, I can accept, actually better, I can accept the alternative hypothesis as a better alternative than the null hypothesis. If I don't get that 95% as a minimal standard, if I get 94%, all right, scientifically, it's not considered a standard, it's not considered significant. So imagine, is that rigorous? Yes, that is fairly rigorous. We can add, an adjective to it. It's rigorous because it means that I need to get that result in the lab 95% of the time in order to claim significant difference from the null hypothesis. Otherwise, the null hypothesis stands, which is the typical null hypothesis, because it's an equal sign, right? The typical null hypothesis means there is no difference. So imagine this, think about it conceptually. I'm doing an experiment and I get the same result in this experiment 94% of the time. That's still not significant for science. So 95% already is a high standard as far as, in society. But even that 95% is only the first level of confidence. It's the minimal level of confidence. The next level of confidence is 99%, right? Now let's translate 99% to the p-value and to the alpha. So what is 99% in alpha? Exactly, it's what is the complement to 100%, right? The complement meaning between two numbers. If I say 95%, what is the complement of that to 100%? 5%, right? Okay, so that's the first level. The next standard of rigor, all right, is I'm saying 99% of the time. So the complement of 99% is going to be 1%. And then we just need to translate that 1% into a decimal, right? Which is, right, 0.01. Or, you know how in science we like to crunch things and say the bare minimum, we are minimalist in that sense. Anything that is extra information we tend to eliminate. So think of the dot. Two zeros to the left of the dot mean nothing, and therefore we omit it. We just say 0.01. Now zeros to the right of the dot are meaningful, okay, because they determine decimal, centesimal, millesimal. So we just say 0.01, all right? That's the second level. And so the alpha for that is 0.01, all right? It's a more rigorous, that's the p-value. The third level is going to be 99.9%, all right? 99.9%. So the complement of that is what percentage? 0.1%, 0.1%, you're right on it. So we translate 0.1%. This is where people get stuck, you know, because we have a percentage decimal. Translate that into pure decimal, right? 0.1%, we have to divide that 0.1 into 100. So in pure decimal, 0.1% is 0.001, because 100, denominator, is going to add 2 zeros on the decimal, right? So 0.1% is, in pure decimal, 0.001. That's the third level standard, right? Which is the higher rigor. And typically that is used, for example, in human trials for medication, for drug research and things like that, where we need a very, very high standard because human health and human life is at stake, all right? So what I'm trying to say is that the degrees of freedom, right, or the confidence level is very important, very significant, depending on the rigor that we want. And from this discourse, then the basic rigor, bottom line, the basic rigor for science is going to be an alpha of what? 0.05. 0.05, that's the basic minimum, which is that 95% confidence level, all right? If I want the next level, kind of intermediate, the 99% confidence level, then my alpha is 0.01, right? And the higher standard, the third degree of confidence level, right, which is very rigorous, is going to be
0.001.
the alpha 0.001, right? Those 3 zeros. And
Yeah,
one.
it's 0.00.
No, because it's 0.1%.
Oh, so
It's 99.9. So it's got 3 zeros.
Yeah.
And then you see, okay? And that's the p-value that you see on the return when you do when the computer crunches the stats for you, when the software, when the technology crunches the p-values for you, you see that value. P equals 0.0001 or 0.7, for example. You know, what is 0.7 translated into a confidence level, to translate into percentage? Yes. So it's a very low confidence. And that's why the null hypothesis doesn't get rejected with a value that is actually higher than what? 0.05, exactly. So we're using the minimal standard. She's using the minimal standard. It's just that she has not covered, that I know of, the concept. She's just giving you the numbers, throwing them out there, and says, if the number is higher than 0.05, what can we do with the null hypothesis? Fail to reject. We have to accept it. You know, see? And so what she's saying, when we translate that conceptually into something meaningful, is saying, unless we have 95% of the trials significantly different than the null hypothesis, we cannot reject the null hypothesis. That's the standard in stats. And that's what it means. And she's keeping it at 0.05 for now to not get people confused. But I'm just telling you that that's the minimal standard in science, in empirical science. There are higher degrees of confidence depending, again, functionally, depending on what the experiment is about and what we're trying to prove, what kind of rigor, all right? You get this also in industry when they're putting out a new product, et cetera, et cetera. Okay, so hopefully that will help a little to conceptualize the meaning of statistics and why it is that unless we have a 95% rigor in stats and in science, we may not reject the null hypothesis. All right, the null hypothesis stands, which means there is no difference with your 94%, with your 93% different results. All right? Okay, forward. So any other questions, comments, anything? No? All right, let's go forward. You can see that has an apply. Oh, the other very brief mention on ANOVA. Again, it's an acronym, analysis of variance. That variance is talking about variation. We covered that, again, in the fundamental course on evolution, variation, which means variation from the mean, precisely. And the variance is quantifying that variation from the mean. The mean is on the center of the bell curve, and any number that moves away from that mean is a variation, slight or small. Remember, selection acts on variation. Selection acts on variation. When the climate stays stable, right, variance may survive as well as the majority. Variance away from the mean, from the majority, may still survive as long as the climate stays stable. When the climate changes, and notice I'm not using weather, but I'm using climate, which already implies time-wise, long-term, right? Long-term. When that long-term climate changes, selection is going to act on the variance. And on average, this is statistical language, on average, which individuals of any population are going to stand to be selected out, because remember, selection is a selecting out process. It's a killing, it's a dying, it's a selecting, it's a non-survival process, right? Selection. When climate changes significantly, which variants on average tend to get selected out? The ones that are closer or further from the mean? Further from the mean. The ones that are going to the tails. And that's where the one-tailed ANOVA or the two-tailed ANOVA becomes significant. At the 95%, at the alpha 0.05, right? Or 0.01 or 0.001, etc. Those individuals stand a much greater chance of being selected out. It may be that existentially, deterministically, they don't get selected out, but they're at high risk. They're right there at the edge of the precipice. Okay? So that's trying to give some application to stats, into evolutionary biology, and eventually into all the 10 to 20 million species estimated to be on Earth today, including us. Yes, Emma?
Okay, I have a question.
Yep.
I saw a graph like this.
Right.
When she was presenting.
Right.
How come it doesn't have a normal bell-shaped
Okay.
curve and it's like this on the X and Y axis?
All right. So the graph that you're showing, oh boy. Bring it up for a moment if you don't mind. The easiest way to do this is just put it on the camera. Let me see if this is going to show. Okay. So showing this on the camera. Hopefully it picked it up for a moment. Yeah, so that's, were you able to see it, Monica?
Yes.
Oh, okay, good. So we got it recorded. All right, so you notice that, is that the first question is it a standard, is it a normal distribution or not? Is that normal or not normal? It's not normalized, right? It's skewed. So it's not a normal distribution, it's a skewed distribution. And where is the handle of the pan?
The slope is going to the right.
Slope to the right. So it's skewed to the right. All right, so it's a one-tail skewed to the right, basically what it is. Because she was talking about ANOVA. All right, that would apply. So there's more variation, basically, how to translate this into biological terms. Is there more variation to the right or to the left of the mean, of the average? Think about it too. It's very important to be able to give meaning to graphs and histograms and figures, all right? Because scientific papers, in principle, a good scientist could interpret the paper without reading the text, just by looking at the graphs and the figures, okay? That's, yeah, because they're informative. And you notice that, you know, from months or years of research, the scientists will select the most significant data. And those are the basis for the graphs and the figures in the paper and in the article. So, basic question. On a skewed to the right curve, which is what you showed, right? Histogram. What is the, where is the greater variation or the greater variance, if you want to put it in statistical terms? Think of the mean. The mean is going to be where? Where the curve peaks, right? The bulge, the highest peak, that's the mean, that's the average, right? So you can draw a line straight down to the x-axis. Where's more variance, to the left or to the right of that peak, of that mean? To the right. That's why it's variant to the right. It's skewed to the right. There are more variation, there are more variance. Think of individual heights or whatever, animals. Translate it into something concrete, determined. Make it deterministic. You know, there are more variance on the right than on the left of that curve. And so it's skewed, and there are stats to analyze that. All right? Okay. Enough. Get back to energy.
Perfect.
All right. So I just need to, yeah, go into my PowerPoint here. Okay, so today we're talking about energy. And again, if you have any questions or comments from previous lectures, let me know. All right. So let me back up for a moment. We started just a very brief synopsis so far. We looked at the formation of the Earth, accretion, right? These words have meaning. The accretion disk, and then for the planetary system, and then the accretion of the planet, planetary accretion for Earth, which occurred approximately how long ago? Put some numbers on it. 4.5, rounded off, globally 4.5 billion years ago, right? Which is 10 to the 9, all right? And for the bulk of that time, the Earth was cooling down because it was a ball of fire, red hot fire, and it cooled down enough. It then took about, how long to cool? Essentially when we start getting crust, and soon, very soon after the crust in geologic time, we start getting life. So it took about 3.5 billion years for the Earth to cool. So the bulk of it, we were just a hot ball of fire spinning on its own axis and spinning around the sun. Eventually, we dissipated heat enough, entropy, right? Enough heat out to the universe to get a crust and to get the 3 basic layers, the crust, what goes into the crust, underneath the crust, the molten stuff that we're floating on, mantle, and then at the core, the iron core, solid core of iron, which is the most abundant metal on Earth, down there, not accessible to us, not yet anyway, not in a long time, predictably. But anyway, that then, because it's fairly dense, generates a gravity that keeps the atmosphere in place. And you can imagine, so think about it, again, conceptually, the core of the Earth is keeping the outermost layer of the Earth, which is gas, in place, right? So very exciting, the different forces that are at work here, like one of the fundamental ones of gravity. At any rate, then we have soon after that, about 3.9 billion years ago, we get some trace. There are some fossil records of bacteria, and some of these become cyanobacteria, meaning that they can photosynthesize and they start changing the atmosphere of the Earth into more and more oxygen significantly for life as we know it. That uses respiration as a means for obtaining energy, all right? So that leads us into, well, the 3 layers, the atmosphere, the hydrosphere, and the geosphere we saw. But significantly, we landed into the crust of the Earth and also the oceans in combination with the atmosphere, which is another fluid, a much lighter fluid. we have the possibility of life. And then we looked at natural cycles. So we look at biochemical cycles of the main elements, like, or the main molecules of life, which are going to be water, carbon dioxide, or some kind of carbon, and then also oxygen and nitrogen. So these are the four main elements that also form our bodies, right? About 90%, I think, of our bodies, or 95%, is either oxygen, hydrogen, carbon, or nitrogen. Okay, so you can see now we're going to look at the other aspect of life, because this so far has been mostly material life, all right, including the elements. Now we're going to go look at kind of the converse of life, which is energy, and the need for energy for human survival and human flourishing. So today's lecture, bottom line, is going to be on energy and energy sources for human flourishing. Okay. Oh, we also looked at cycling last lecture, and including recycling waste, not human recycling, but recycling the waste of humans, as kind of a summary of that material world, if you will, the material organic world. Okay, so in energy, this is what we're going to be looking at today with regards to energy production and consumption. And some of these are going to be renewable sources and some are non-renewable sources. All right, so just going down the list, for today, we're going to look at fossil fuels, nuclear energy, then solar, wind, hydroelectric, geothermal, wood biomass, biofuels, other creative sources of energy that are being exploited today. And then finally, to put in the bioethical analysis proper, the natural right to energy, the human right to energy, because without energy we cannot flourish, and landing it with Pope Francis' statements on energy and action on energy as recently as last year. Okay, a conference that he was able to bring together major CEOs of the oil and coal producing companies in the world at the Vatican, and a conference at an international conference last year, or international dialogue, and some commitments from these fossil fuel industries, which their budgets are possibly billions, if not trillions of dollars, okay, annually. Forward. All right, so we have two main types of energy sources, either non-renewable or renewable. Interesting that on the non-renewable, fossil fuels and nuclear, essentially, whereas in the renewable, a much greater variety of sources, solar, wind, hydroelectric, geothermal, wood, biofuels, and then others, there's a much greater variety of renewable sources, but still quantitatively, the bulk of the energy sources for humans today is still non-renewable. All right, so it's a work in progress, but we can say that gradually the transition is happening. Then it depends what part of the world, and there's kind of a link here. If you follow, you can follow the trail or the links on the chain. We can begin with nature, and then, because one way or another, it is nature that is supplying the energy source, right? And then from nature will be technology to exploit that nature one way or another. When we talk about technology already, it means economics, right? The market economy and the business world. So there's economics involved in technology. And as soon as we mention economics, then the next layer is going to be politics. And politics associated with society, and whether we have possibility of influencing the politics of the nation or not. And that again gets very fragmented in its body around the world, because some politics are more participatory than others, right? And we have the full gamut from the best democracies in the world to the worst dictatorships in the world. Okay, so gonna look at non-renewable first, and the biggest one by the number is fossil fuels, which come in 3 varieties, depending whether it's solid, liquid, or gas, but they're all variants of the same original source, which is rotten forests, thousands and millions of years ago. And so the 3 states are going to be coal, solid coal, liquid petroleum, as thick as it is, it's still fluid, and then natural gas, right? So coal, petroleum, otherwise known as oil, just in common language, coal, oil, and gas, meaning natural gas. These are examples here. This is strip mining, which essentially takes down a whole hill or mountain because it happens to be a mountain of coal. So that represents a lot of money for the industry because it's still the cheapest source of energy is burning coal. This one is an oil rig or platform in the ocean somewhere. And so oil can be extracted from land or from ocean, meaning, and this pipe may go down maybe half a mile, 1 mile, 2 miles into the ocean to get that oil, and then it goes further down 1 or 2 miles further into the floor of the ocean, the ocean floor. So you can imagine the expense of doing that drilling, and yet it's still profitable, highly profitable, meaning that petroleum oil is still highly desired today because it's one of the cheapest sources of energy for mostly for industry and transportation, many other things that we'll see today. This is a coal plant that is crunching that oil, coal and essentially generating electricity, all right? So most of this is for electricity. When you see these towers putting out all these fumes, it's important to understand that these fumes are not, that's not CO2, all right? What is this typically? This is water vapor. In fact, typically for water vapor, what gives it away is the gap in between the chimney and the cloud. You see that typically there's a little blank there, there's a gap, right? What is that gap? That gap chemically, physical-chemically, is the water vapor that is coming out here is so hot that it's still transparent. When it starts condensing into a cloud is when we can see it. But the vapor itself, it's a gas. So we don't see gas with our eyes unless the gas itself has a color, all right? But water gas, we don't see. It's only when it starts condensing that we actually see it. We see the tiny little crystals that are forming there, and that's the water vapor. So if this were CO2, for example, we'd see the CO2 directly, immediately from the chimney out, all right? And it would typically go further up instead of sideways. Anyway, my point is that at least in industrialized nations, nations that have regulation and control over industry, right? And that regulation is more or less applied instead of corrupted and paid off, then these stacks that you see and this whole bunch of fumes being poured out, that's water vapor. It's water vapor that is essentially going into clouds, all right? So it's not harmful. Different would be if this was actual CO2 that is coming out. Now, CO2 may well be coming out in some industry in other parts of the world, typically in developing countries where there is either no regulation or the regulation is simply not applied because of corruption of the human heart. Okay. This one is mostly, I don't know if this is actual petroleum or natural gas. It could be a gas refinery, but the same, all 3 states are refined typically to generate electricity. It's the main issue to put it into the grid, right? Okay. So let's look at all 3 in a little bit more detail. Coal, here are the piles of coal that is brought in either by train, by trucks, or by wharfs, large boats on the river. It is burned at some point, and the burning heats up water. The water that is heated up will go through a turbine. It's actually the water, the heat up water turns into steam, and it is the steam that turns the turbine to generate electricity. And that electricity is pumped into the grid, all right? And so what I want to point out significantly that this core aspect here, steam turning a motor, steam turning a motor. This is called the steam engine. And this goes back about 300 years to the Industrial Revolution, which was the beginning of modernity in a technological sense. This allowed, essentially got rid of what is known as cottage industry. Cottage industry was making things by hand, which was the standard before the 1700s, all right? And then at the end of the 1700s, we get the invention of the steam engine, which is a quantum leap because now products can be mass produced in series. It was a huge to-do for labor because labor was displaced slowly but surely and sometimes rapidly by machines. And instead of the labor, the human being doing the thing by hand, either carving a chair or whatever it was, now the human being was being replaced by machinery, and the new labor was the human taking care of the machinery, but the product itself was made by machinery. And typically the steam engine, which generated industry, mass production of things. So the cost of products went way down for sure, because now you didn't have to pay a craftsman for carving out a whole chair. You can produce, in the same amount of time, you can produce hundreds of chairs and just pay the person who's maintaining the machine that makes the chair, all right? When you add plastic to this equation, then it accelerates it even more, because with plastic, you can mold things and it can be mass produced very fast and so forth. But this was such a huge to-do that it generated, from the Catholic Church perspective, the first, what is known as a social encyclical of the church, which was in, I believe, 1798, Rerum Novarum of the New Things, the title of the New Things. Rerum Novarum is known as the first social encyclical. Go back, it was Pope Leo XIII. I want to get a date on it. Let me go back here for a moment. 1891. Okay, 1891. Yes. And it is the first reaction, if you will, to the Industrial Revolution that already had been going for quite a few decades, since the beginning of the 1800s. And essentially the replacement of human labor with machinery, and then the enslavement of humans, of the workforce, into industry, where originally there were no regulations. There was no minimum wage, there were no safety. People were losing fingers, legs, heads in the machinery, and some of it so drastic, but fumes inside. No regulation for industry, basically, because it was always, the regulations were catching up with the mass production, all right? And so this is known, it's a watershed for modernity, if you will, coming into the 1900s, as you can see, with the first encyclical on social justice, all right, on behalf of labor, including to the action, the social action of organizing labor so that they would have some political power against the empresarios and the owners of the industry, which were the unions, the labor unions, all right? Which kind of, they were already crass guilds of craftsmen, the people who worked the wood, the wood carvers, the metal workers, and so forth. There were already guilds in the Middle Ages and so forth, and the Renaissance that were also organized by the Catholic Church to give them some clout and organization and so forth and structuring. But that transition into the labor unions in the 1900s and the labor strikes. So these were huge social movements that happened in the 1900s, the early 1900s. And so it has an ethical meaning also, an ethical relevance. Eventually the unions became very secular and in some places too powerful or very powerful, and it was hurting the economy, so there had to be regulations back and forth. And the bottom line, it's all in the dialogue, right? It's all in the dialogue, but even lobby groups, for example, that are in Washington, they're very powerful. For example, AFL-CIO is a huge international powerful lobby group and labor force. The syndicates and all that came out of it. Then the mafia got into it too and started manipulating the syndicates. And so you can see it's a very complicated history in the past 200 years, very turbulent, and all because of the steam engine, right? Getting vapor, water vapor to do work and translate that work into generating electricity. Interesting. What's at the other end of so this is the clean end, if you will, of the burning process is steam, right? Just like the steam coming out of a teapot. But the nasty end, the dirty end is the byproduct of the burning, which is going to be typically CO2, which somehow has to be either trapped, captured by filters, and some of it may be released into the atmosphere. So the crunch is going to be here at the filter, which ironically, these filters that trap CO2 gas, which was the major offender of the 3 or 4 gases that are greenhouse gases, right? So the 3 main ones, CO2, methane, and nitrous oxide. I'll get to them a little further down. The main one by far in quantity and effect, well, actually methane is more heat absorbing, but lesser in quantity. CO2 is the biggest one. It's the biggest one. What traps CO2? Gas, these filters. It's known as activated charcoal. So charcoal is coal, right? Activated charcoal, all right, meaning that it has polarity, it traps the CO2. So it's interesting that carbon traps carbon. Okay, so solid carbon is trapping gas carbon, and in a sense, artificially, man-made sinking, if you will, man-made sinking of CO2 with these activated charcoal filters. And you can take it all the way from industry down to the home or charcoal filters that are used in labs and so forth. The labs in this building upstairs, they have hoods, and those hoods in the organic lab have charcoal filters, activated charcoal filters that are EPA regulated, and they have to be changed periodically, and there is all kinds of regulations. If those filters are neglected, the building is shut down by the government, okay? The Environmental Protection Agency, because we're caring for the environment. So there's extra money put into those filters, but it protects the environment. So this is a loss, if you will, from the industry, but the idea is that they get more profit out of the net profit out of burning coal. So they have to include the loss, the cost of production cost of the filters and so forth, abiding by regulation. Okay, that's when the system works. Fracking. Fracking is controversial, and we're going to look at it in some level of detail because it started in the 1990s, I believe, and it's innovative. It's trying to get more, mostly gas, natural gas, out of rock, but also some petroleum can be gotten out of that. So fracking is a crunch word representing hydraulic fracturing. And what is fractured is the rock, a particular type of rock that is called shale, all right, and also coal. So let's look at coal for a moment. Well, look at this horizon here. Look at this cross-section of a typical landscape anywhere in the world, anywhere USA, the Midwest, for the sake of being flat, the Great Plains, all right? You have the surface of the earth here with these fracking bores and also water bores or holes. This is just a fancy word for hole. Let me make this bigger. And slide it over so that we can see it better. Yep. Okay. A little better. All right, so what do we have? We start at the surface with drilling down, sometimes 1-2 miles down. The water bores, the water holes are going to go into the aquifers, which are at several layers down into the rock. So you see we got first the topsoil, the top layer is mostly soil, can go for several feet to several hundreds of feet of soil. It's the topmost layer. This is mostly organic material, decayed organic material mixed in with minerals, all right? Different types of soil, etc. All right, so life occurs at the surface of this and embedded a little bit. Below the soil, typically we're going to hit sedimentary rock, layers and layers of rock, which is porous and cavernous, meaning with holes in it. And those holes are typically filled with water, groundwater that has percolated, remember the water cycle, all right, into the sediment where it reaches a fairly impervious layer. It's going to start settling there, the water. So this creates various aquifers. Some are shallower, some are deeper, okay, depending if it's old water or new water, because this thing is also in some of a dynamic state, and periodically some cracks or fissures can occur that will leak water, because water is forever following what? Attracted to gravity, right? Remember, it's filling the container, and if there's a crack in the container, the water will go down that crack, okay? All right, so the natural forces are at work here, the fundamental forces. At some point, when we go deeper down, 1, 2, 3 miles, we hit at some point in some places of the earth and in the United States, including the Midwest, we hit this layer of shale and coal. Coal, which you see, coal is kind of packaged in between these layers of shale, all right? So coal, what is coal? Coal is a rotten forest. It's a humongous forest of old that got crunched and putrefied and almost crystallized, became hard rock, all right? And that's coal. So coal is basically rotten forest, which is mostly vegetation, mostly tropical when the earth was tropicalized. Remember, in the interglacial periods, of which we have at least 4 in the last 500,000 years. 500,000 years is not that long geologically, right? 500,000 years. And so these tropicalized earth had these huge forests, mostly in the northern hemisphere, all the way up to, remember, in tropicalized earth, there was no poles. The interglacial periods, full interglacial, all the ice was melted. We had essentially no solid water. It was liquid, all right? And so the temperature was warm and humid, and it generated huge tropical rainforests. Yes, including all the animals that were in it, including the dinosaurs back several million years ago. And then we went into winterization. All those forests died and got sedimented eventually with layers of soil and minerals and dirt, so forth, got compacted into the earth and it started rotting, and rotten forests eventually become, to give it enough time, typically millions of years, they become coal, a black solid rock, all right, that is rich in organic material that is embedded in there. All right. Now, some of that I missed a in-between step. Before the coal, we had the gook, the black rotting gook, which we call petroleum. So the forest, when it starts decomposing, becomes a gook, for lack of a better word, which is petroleum. It's highly organic, rich in organic material, which means it's very combustible, right? And when that petroleum seeps down and continues to get crunched, eventually it solidifies under tremendous pressure and becomes coal. That coal is very organic, has a lot of, you can actually, for some coal, you take a chunk of coal and light it up and burn it, the actual rock, all right, because it's very rich in organic material. So that's coal. Then the shale is a mixture. Shale is kind of an in-between layer between sedimentary and the actual solid coal. And shale is porous and is full of petroleum and gas, natural gas. Because the decomposition process continues, even that deep further down, there are bacteria down there, and the petroleum decomposition continues, and a byproduct of the bacteria, a burping of the bacteria, is going to be the natural gas. All right, so natural gas and petroleum is trapped in the shale. Coal is more solid, and therefore, I really don't know exactly if some coal may have still some petroleum and gas trapped in it. Don't know. Well, here by the fracking, it would. But the fracking is going to be done in the shale layer and in the coal layer. So yes, it would have some petroleum, especially gas that gets trapped in there. So it's a mixture. This is what fracking is. They drill down, I'm saying 1, 2, 3 miles down, and then they drill horizontally. When they find either a shale layer or a coal layer, they will drill sideways, again, 1 or 2 miles sideways, horizontally. And that horizontal drilling, that horizontal tube, right, tunnel, that's what's going to do the fracking itself. The fracking, again, is hydraulic fracturing. The hydraulic part, the fraction, is trying to fracture, is trying to shape that layer of shale, is trying to shake that layer of shale, sensitive. See here, this would be like the layer of shale that has its fractures in it. And in that fracture, think like a sponge that is hard, but the sponge is saturated with petroleum and natural gas, all right? And so it's trying to continue these fractures, to continue to shake it up, because it's kind of unstable down there. You know, it's if you fool around with these layers, you can shake them to get some petroleum and some gas out of it. And the idea is that brine is pumped in there. Brine is salty water, water that is dirty with minerals, okay? And is pumped in there, and to try to shake that up and get into the cracks. And that brine also has some sand in it. So it's really, it's a combination of a solution and a suspension, right? And it's pumped back down in there under pressure to get into those cracks and to open the cracks, the fissures, down to a very fine level. And the net idea is to have the gas from there escape and mix into the brine, and then recover that water now that has, or the fluid that is going to be saturated with gas, natural gas, and perhaps also some petroleum that gets dissolved or suspended in there. And then that is pumped back out, and that is what is processed through a refinery. Okay? So that's the basic concept in fracking. Again, it's hydraulic fracturing. So the fracturing is trying to fracture this shale and coal layers into releasing its natural gas and perhaps even some petroleum that will get dissolved in that brine and then pump back up and refined, recover the organic material in it, mostly natural gas. The fracturing does cause some seismic waves, but they're minor, okay? So the claim that is causing earthquakes at the surface, it's an iffy claim. There are some tremors that may be produced from the shaking up of these layers, but these layers are so deep that typically, if there are tremors at all, they tend to be minor and not significant, at least that's what the industry is claiming, to disrupt lifestyles at the surface. You know, they're not major earthquakes that occur along the West Coast from the rubbing of plates, of tectonic plates, all along the, for example, you can think of the Pacific Rim, the Ring of Fire, all the way the Rockies, California, you know, the famous San Andreas Fault. They take it down to Mexico, even Mexico City. I've been involved in, when we lived as teenagers in Mexico in the 1960s, I felt some tremors in Mexico. That's inactive, but those are tectonic plates that are not being produced by this. Okay, so very different from these things, which tend to be light if there are any tremors at all. So controversial. More significant for possible contamination along the way is that there could be some explosions that occur because it's organic material. This is a general risk of blowouts that can happen for any rig of petroleum, all right? Even on land or in the ocean, as we saw with the Deep Horizons rig that exploded or caught on fire there in the Gulf of Mexico a few years ago. Remember that the biggest oil spill in the history of the U.S. Into the coast of Louisiana and so forth. We saw a little film on the grass that was regenerating that coast. Okay, let me finish here for a moment here. And then other downsides or negative aspects of it could be that some methane is released, and methane is a greenhouse gas, and my understanding is actually more greenhouse than CO2, right? It tends to retain more heat, but is much less abundant than CO2 in the atmosphere. And so that's a concern there, that there will be leakage, and that methane, as it's being leaked out through, it would be leakage, imagine, through all these layers. So that leakage would also mix in, some of that will mix in to the water table that can contaminate, may contaminate the water that eventually is used in drinking water, all right? So that would require then filtering systems and monitoring the groundwater for being clean and not contaminated, because the standard now that basically when you get into the aquifer, that is typically clean water. It may be high in minerals, but it generally is safe to drink. For example, here we have what is known as hard water. Hard water, the pH can be around 9 or 9.5, which is very alkaline, but that shows very high in minerals. But it's drinkable water in the sense that it's not contaminated with toxins or bacteria, because the layers of sediment have actually filtered the water naturally as it percolates through the layers. And we have a well here. I've actually drunk well water. It's not too tasty because it has a lot of minerals, mostly iron content, and also some sulfur. So you get that egg, the rotten egg smell of the sulfur, right? Light, but it's there. And the iron also, you can taste a little rusty on the water, but it's high in minerals, so it's actually healthy. But it is drinkable because it's not contaminated with toxins or bacteria, stuff like that. Okay, so to finish that discourse on the water table and the water here in South Florida in particular, and Miami, which we tap into what is known as the Biscayne Aquifer, there are water treatment plants in Miami and Dade County. I've visited some of them. And the water treatment plants, the main action of the water treatment plants in Miami, in Dade County, since they're tapping into the Biscayne Aquifer that is generally drinkable water, is to lower the alkalinity, to bring it to something that is not hard water as such, because with hard water, you cannot get foam, for example, on the soap, you don't get suds. So these typical, the water treatment plants in Dade County, typically they soften the water to about 8 or 8.5 pH. 7 is neutral. So they bring it down about one degree pH so that the water is less hard, a little softer. And in that process also get rid of the bad tasting and bad smelling stuff in the water. Okay, and then the other aspect is that, so this one indicates here the possibility perhaps it may require some purification of the water, or at least monitoring the water table for potential contamination, either through methane or through other gases that can, even the organic gases, natural gases that can percolate out into the water table and contaminate that, right? So that is a concern, because that water table is typically used for towns and for cities for drinking water at some point, and also for irrigation, etc. So that's fracking. Now, it's still controversial, like I say. It means, in my mind, in my estimation, bottom line is that the industry, since they're getting money out of it, millions and maybe billions of dollars, they have to reinvest into making it safe in different ways so that they don't contaminate the water table and so forth. So it's going to be more sophisticated technology to monitor the whole process so that it doesn't contaminate, or minimizes the possibility of contaminating the water table and also the atmosphere with the methane and so forth. Okay, stop here. Questions or comments? Monica, I'm sorry, Hema, you had a question?
Yes, Father.
Mm-hmm.
For the drill, how do I manipulate it to go horizontal like that?
Exactly. Very sophisticated technology, right? It's amazing. Bottom answer is I don't know how, but they have a way of how to do that with the heads of the actual drilling bits, which sometimes you see this, they're like 3 gears that grind into each other. And as they grind into each other, they grind through the layers. So very, very sophisticated technology that goes down there. The investment is probably in the millions of dollars for the technology, but what they get out of it, they have to get a profit. Otherwise, they wouldn't invest millions of dollars, right? So if they invest in millions of dollars, but they're getting hundreds of millions of dollars out of it in the product, then it pays off. It pays off. So all I can say is very sophisticated technology, engineering, geologic engineering, which is a big field, is industrial, all right? And it's sophisticated. Alloys is one aspect of this. What are alloys? Alloys are combinations of different metals to have particular characteristics, okay? One that has been that was discovered, I want to say, thousands of years ago. I don't know if it's the most common alloy, but I can say probably the most useful alloy that launched civilization into a whole new era, humans, all right, from a very primitive prehistoric condition into a much more sophisticated type of society, is bronze. Bronze, which is a combination of what? It's a combination of, copper and I think it's tin. But the Bronze Age was very significant in the history of humanity. Copper with tin. Yeah. So we went through. So tin is a metal. Tin looks similar to aluminum, more or less. Okay, it's pliable and tin is used a lot in pipe organs because it makes very good sounds. But it's kind of a grayish metal similar to aluminum, more or less. Okay, yeah. Anyway, first copper was discovered because it was more visible and it's also pliable and so forth, and it has conductive characteristics, etc. But at some point, some primitive humans realized that mixing tin and copper together, melting them both and mixing them, gives a much harder metal, which is bronze. And I can tell you that a lot of the weapons in ancient civilizations were made out of bronze. And a bronze spear or a bronze arrow, for example, a bronze sword is much more effective and much harder, and you can get it much sharper. It will hold the sharpness longer. And that's on the military side of things. But then on the utensil side of things, bronze, you can make it for vases that would last centuries. We have bronze vases that have been made thousands of years ago, and they're in museums and they still hold their shape. And so bronze was a huge step forward, even up into the Industrial Revolution to today. Bronze is still used in a lot of machinery today because it's stable, it holds its shape, it's hard, it's easy to produce, etc., etc. Okay, so that's just an example of an alloy. Today, there's a whole field of alloys, mixing metals and even metals with non-metals to see what the product is and what characteristics it has. And the typical thing is, for example, it is much stronger, much lighter, and so forth, more conductivity, it has particular properties, all right? And so alloys is a whole new field, and alloys are very involved in the fracking industry and in the fossil fuel industry, right?
And it doesn't rust, Father?
Some have that characteristic, that it doesn't rust or it rusts very little and so forth, yeah. Mm-hmm. Whereas copper is highly rustable, right? I don't know if that's a word, but copper rust, typically rust green. Mm-hmm. But that's copper oxide, okay? That is being wasted, it's even toxic and so forth. Okay, other questions or comments?
I just wanted to make a comment.
Yep.
When I was on the ship,
Yep.
They had, I don't know what it's called, but we have to shine it.
Yep.
I think it's made of copper that hold the chain to the anchor.
Right, yes, those are,
I forget what it's called.
yes, yes, winch.
A winch?
It's called a winch, and it turns
Big, yes.
huge. It's a circle, right? That is concave, and it turns, and it pulls either ropes or chains in ships and boats, and it's used a lot in sailing and shipping, and those are winches. They're typically connected to a motor, and they, depending on the loops that you put around that winch, the power that you can get out, you can raise huge anchors, move sails with it. The sheets are the lines of a sailboat that move the sails. Yeah. Okay, so a lot in that industry, right? Still controversial. Let's look a little bit at the distribution of coal. The distribution of fossil fuels. Specifically petroleum. The distribution of petroleum into various products. We can see that about half of it turns into gasoline, all right? Then about 1/3 goes in, about 1/10 goes into jet fuel, and then another 1/4 into diesel and other fuels. So if we add these 3 types of fuels, gasoline, jet fuel, and diesel, it's about 85% of petroleum is refined into fuels. All right? What does that mean functionally? It means that the gook, the black gook, has these fluids in it. a fluid that is highly combustible, that can typically run pistons, and it can be used either for burning, for steam, for the steam engine, or the piston engine by the combustion that occurs in the pistons, right? By burning little tiny amount of that fuel, either gasoline or jet or diesel. So we can say that the bulk of petroleum to this day is being used for fuels to move machinery, transportation, etc. And the other 15% is distributed into things like asphalt, oils, lubricants, and other products. What is this other products? Mostly plastic, right? Plastic. So this last 10%, petroleum, is mostly plastics of different kinds. And that's why plastic is flammable, right? Because comes originally from a rotten forest.
Yeah, Father, you know that I have a friend that lives in Spain,
Mm-hmm.
and he wanted this cream for his baby.
Yeah.
So he didn't find it there.
Uh-huh.
So he asked us to see
Right.
if he could buy it in Amazon and we can send it to him.
Uh-huh.
So we did,
Yep.
and in the border of Spain, they didn't let it pass.
Wow.
And they returned it. So I was like, what? So I started searching,
Yeah.
and the things that the cream
Uh-huh.
has, this component is plastic. It
Yeah.
has petroleum, basically.
Right, right.
So the regulations in Spain, they don't let them use the.
Look at that.
type of
Tremendous. Yeah.
cream. So I started researching, and a high percentage of beauty products here, they have plastic and petroleum.
Yes, yes, they
And a
do.
minimum percentage, but they have.
Very tiny.
And
Mhm.
it's cancerous to use it a lot.
Exactly. So mine is first time I hear about it, but it's an interesting news. And in principle, I think it's a good news. It gets into the bioethics of it. But so what do we have? It's called petroleum jelly. Petroleum gel. Petroleum gel has been used for decades in the industry as a base, right? In which they embed whatever product, the active ingredient of the product. And it's in many, many things, including cosmetics. Now, one alternative to that is algin, or which is basically, I think it's mostly collagen protein that comes from algae, all right? Mostly pheophytes, brown algae, kelp in the Pacific Ocean. But that apparently is a little more expensive to produce, or much more expensive, I don't know, but that's organic. And that would be more friendly to the environment if it's based. And that's used for eating products. For example, Jell-O. Jell-O is mostly algin. It is this collagen protein that serves as a scaffolding. And then in that scaffolding is embedded microscopically the flavor and the color of Jell-O, and many things are edible. But then on the non-edible side of industry, the creams typically have a petroleum gel as a scaffolding basis in which the active product is embedded, right?
I think it was the newest petrolatum, something like
Petrolatum, yes.
that. Yeah,
Mhm.
something like that, but it was interesting because it says that in Europe,
Mhm.
you cannot use that for cosmetics.
Look at that, in Europe in general,
Yeah,
exactly.
and the European Union.
Right, exactly.
So it was like, there are like 80 components that
Right.
the US use.
Right.
But in Europe, you
Look at
cannot
that.
use for products.
Wow, tremendous.
For the consumer use.
It's exactly.
So
Wow.
because of the
Mhm.
regulations, the politics are different.
Exactly, yes, exactly.
And in
So what
fact,
do we
they
have?
returned the cream. They didn't.
Right? They didn't confiscate or
And it was
anything, they
a baby,
returned it.
a cream for baby rash.
Yes, yes.
And they
Something
returned
that
it
would seem
because
innocuous,
they
yeah.
didn't let it in. So I was
Right.
like, wow.
Right, right, yeah. So exactly. So what happens is, remember that in Europe in general, that was part of the union thing. They tend to have a greater social conscience than we do, all right, overall. And they're more concerned for the environment. Also, their population density is higher, and so they have to be more concerned for the land and not contaminating. And also the Mediterranean is mostly a closed sea, and a lot of stuff dumps into the Mediterranean on the runoff. So they're very concerned about these things. Remember, the films that we saw on microplastics and microfibers and so forth. So they're very concerned about that, and they're trying to be proactive about it and trying to be more eco-friendly. So on that aspect, I applaud them for that. The downside is that I see is that the more eco-friendly that nations become, the more pro-choice they become, for lack of a better word, the less regard for the unborn, and the more they tend into euthanasia or physician-assisted suicide, which are topics that we have covered. So to me, it's very paradoxical that they can be so concerned for the environment and so liberal on the human life issues, especially the two most vulnerable times of life, which is the very beginning of life and the end of life. And it's very sad, and the church position is kind of the third way, which is trying to be both environmentally responsible, but also responsible with regards to human life and the two most vulnerable stages of our life, the two most delicate stages of our life, which is the very beginning and the end, all right? But yes, so I see that Europe in general is much more sensitive. They don't allow, for example, meat products many times in Europe from the US. Why? Because here we use hormones, the artificial synthetic hormones for animals to grow them. I mean, we have to be real. A normal chicken, the original chicken, is not the size of chickens today. Chickens today look like a small turkey. Okay.
They even fall because they have this huge,
The breast, yeah, the breast muscles
I
are
watched
so,
a video once,
Mhm.
and the poor chickens, they couldn't
They couldn't
walk.
sustain it, right? Exactly, and they're cooped up and all that. So on various counts, so the one count is on the hormones in the animals that they don't want, the Europeans don't want to be eating that stuff or passing it into the environment. And the other count on the cruelty thing.
Yeah.
Just as recent as a couple of days ago, I saw the Germany, since we're on this, we get sidetracked, but it's all right, it's graduate school. Let me
It's funny
see.
in a way because, but it's cruel. It's
Exactly. So it's inhumane. It could be inhumane for the chicken. And so this chick, Germany, culling, shredding. Yeah. Okay. So this was in the news just a couple of days ago. Throughout the world, billions of chickens, male chickens, are killed every year. Male chicks when they're born, because this is what happens. It's the female that can get fat. Yes, and so the males don't get as fat as fast, and so the male chickens are discriminated, and the industry doesn't have a purpose for them, and so they're killed, right? And they're killed in two ways. I just saw this news a couple of days ago in Germany. They're killed either by gassing them, right? Or they're killed by shredding them.
yeah, chicken nuggets, I think.
Uh,
Watch a video.
Well, I think the shredding is not edible, but it can be used as feed, or it can be used as right. So the Humane Society equivalent in Germany has been after the industry for some years now to find a more humane way of doing this, or sparing the male chicks from being killed as soon as they hatch, all right? And so it got political, and it had to go through some kind of a government review board that gave permission to the industry temporarily to continue to do the killing of the male chicks until they find a better solution, because they realized that it's not, it's on the economy, how feasible it is to do something alternative with the chicks, or to perhaps kill them in a more humane way. I was reading in the article that, ironically, so the intuition is, what's the intuition? If you're gonna have to kill the chick, the male chick, which we could justify bioethically, for a reason, for a very serious reason. The very serious reason supposedly is so that more people can have chicken available at a reasonable price, right, to eat, which would be the female chick. So how to kill the chick, the male chick, as soon as they hatch, either by gassing or by shredding, right? the intuition is that it's more humane to do it by what? By gassing or by gas, right? If you have to kill the chick humanely, right, or the least inhumane, let's put it this way, intuition would say that the least inhumane is gassing it instead of shredding it.
Yeah, not paper,
Exactly, exactly. So with gassing, it sounds like, okay, they'll go to sleep forever. The other one, you actually are making, bloody organic mush out of them. So, well, the Humane Society equivalent in Germany was actually saying, no, if you have to kill them, it's better to shred them than to gas them, because for gassing, it takes up to a few seconds for the chick to actually die. But in shredding, it takes less than a second. So it's more instantaneous, it's faster. So the chick, if they suffer, or the pain, we don't know if they suffer or not, because suffering is more psychological, but the pain is hypothetically less, or the duration of the pain is less by shredding than by gassing. So this is how technical it gets, right? But the way, it's a temporary solution. Germany in particular, number one, is a huge, strong economy throughout the world, but also they have the background of the Nazi regime, right? And they were gassing humans, so they have to be very careful about when they translate that into animals because of the social perception and so forth, but also for humane reasons. But anyway, these are the issues in the industry that present themselves that are bioethical issues. Okay, and simply, unless we see it in the news, we have no clue. I had no clue that male chicks were a problem, all right, to the tune of billions of them yearly.
No, and it's ironic, Father, because you have so many countries that don't, poor countries, they don't have food.
Yeah.
And they're just,
Right, right.
Type of country they have more.
Exactly. So could we move these chicks out into the developing world as an alternative and have them raise it?
As a donation.
Right.
I don't know, but you can raise those chickens in a regular farm in a poor country.
Right. Exactly.
So
Even though, right. So where does the buck stop? Right. In other words, in a market economy, which is the standard for the Northwestern Hemisphere, which is the most developed countries of the world, meaning North America and Europe and some parts of Asia, right? The bottom line is that in the market economy, as long as they don't lose, better if they make a profit. If they break even, at least they can get the PR of not killing the billions of chickens, and they would translate that into some kind of a positive thing, right? But the bottom line is that if it costs more to ship these chicks out than to shred them, they're going to shred them because it's a market economy, right? It's a market economy. So these are the challenges. But all I'm saying is that when we get creative in bioethics, we could be doing this kind of analysis for the industry in bioethics.
Yeah,
there's a
negotiate like
exactly.
Take it as a donation, you don't pay taxes, or you get a
exactly.
Taxes. There are ways.
So conceptually, a bioethicist who speaks German can get into this industry and English and could get into the research and find an alternative for the industry that could represent savings in the millions of dollars, or could represent savings in the PR, which then that particular chicken they can sell at a fraction of a euro more, and then when that's scaled up, it could be profitable, at least to pay for the salary of the bioethicists who did the work for them. See what I'm saying? So these are industry possibilities, or maybe even on the government side, either side, to do the analysis, or it could be an NGO that has an interest in it and so forth, So these are possibilities. All right, forward, because we're only 1/3 of the way here with the slide. And now for fossil fuels, they're still the biggest offender as far as contamination or greenhouse is concerned for the environment. And we'll come back to a composite chart to see the transitioning from non-renewable to renewable over the past 230, 250 years, more or less. All right, let's look at the other non-renewable, which is nuclear. And in nuclear, there has been a transition. So first of all, nuclear started in the 60s. Mostly from research, military research. Happens that my brother wanted to be a nuclear physicist way back in the 60s. We were both in high school, living in Mexico City. And at that time, around 1968, he went to the States. He came to the States, he finished his high school, and he was good at math and physics, and so he wanted to be a nuclear physicist. And he started researching here in the US, and just about the only university that had a nuclear reactor for educational purposes was SUNY Stony Brook, University of New York at Stony Brook, which is way up in Long Island, all right? You know, the state university system of New York is called SUNY, S-U-N-Y, just like we have a state university system here. Anyway, it's just an aside. But to pinpoint it, back then, SUNY Stony Brook was, from what he tells me, the only university, at least over here on the East Coast, that had a nuclear reactor for educational purposes, all right? Because up until then, nuclear reactors were strictly military because of the power, the potential power, right? And there was, of course, well, all this stems back from 45, the bomb, the hydrogen bomb and nuclear research, which was highly classified at that time. Then we got out of the war into the 1960s. It started getting commercialized to start producing essentially heat to run the steam engine to produce electricity, to generate electricity. Okay, so in the background was still the steam engine. And so to trap that heat by the nuclear fusion, to run the engine, the steam engine to generate electricity that will be pumped into the grid. Nuclear reactors then started taking off, commercial reactors, first and second generations. This is important because those first and second generations had some degree of safety built in, some redundancy in the safety, but not that much, okay? To the point that when the curve starts going into a log phase, right? Meaning ramping up the number of reactors. This is the y-axis is the number of reactors in the world. This is global. We start getting accidents. Now, look at this, from 400 reactors, one accident. Remember 3 Mile Island, way back? You people are probably too young to remember. I remember 3 Mile Island in the late 70s. Okay, was a meltdown here in the US. Then in the late 80s, the big one, Chernobyl, in then the Soviet Union. This correlates to the arms race between the US and the Soviet Union, including military, but also commercial. All right, because there was a two-pronged approach. It was not only military, it's also commercial. What did Reagan do? He took the Soviet Union to the knees on economic because they could not pump in on a centralized economy of the Soviet Union. The Soviet Union was essentially beginning to starve the population because the money was being pumped into the military buildup and the whole arms race. And we outnumbered them with a mixed economy, with a market economy. Essentially, Reagan was able to pump more money into the military that Gorbachev was able to pump into their economy for military. And so they had to surrender, right? With symbolically was the collapse of the wall, the Berlin Wall that divided Berlin from east and west and reunited Berlin into one Germany, right? 1989, I was studying in Rome and went to visit the wall as soon as it fell. I remember people taking chunks. I took a little chunk of the wall that was eventually broken down. There was a very famous passage there called Checkpoint Charlie. A lot of spy novels were made there. Checkpoint Charlie across East and West Berlin during the Cold War, the height of all that intrigue and spy movies and so forth. Anyway, Chernobyl was the second one. close to 500 reactors were active worldwide, and these are all generation 1 and 2 reactors. And eventually, more recently, in the 2011, whatever it was, Fukushima in Japan, partial meltdown also. But still, these were okay. So after Chernobyl, things really leveled off, as you can see, with the production of reactors, either already in active use or in the production stage, okay? So these two curves correlate, as you can see. So it leveled off into the 90s, into the 2000s, and then Fukushima happened also, which was caused by some kind of drastic catastrophe, which was an earthquake and an earthquake and a tsunami. Thank you, that hit the island, which was on the coast because of the source of water that they need for cooling their reactors. And so that got huge publicity and so forth. But basically, what I want to point out here is that nuclear got a bad rap and a bad rep because of these 3 accidents, okay? Out of 500 reactors, 450 essentially that were active and 50 more that were in various stages of construction. So that it's leveled off right now. However, our nuclear physicists are telling us that short term, to make a transition from fossil fuel to renewables, all right, to make a massive, because we need to go industrial, we need to go into the kilowatts and into the megawatts and into the gigawatts if we're going to be generating electricity for entire cities and towns and megalopolis and industry and agriculture and so forth, you know, where the large amount of electricity is needed, then we need large volume capacity for generating that electricity. Nuclear could do it in a relatively small contained area. The footprint is minimal when we compare the amount of electricity that these nuclear reactors can generate for entire metropolis, right? So the transition can be there. What needs to happen, of course, is we need to refine the generators, the reactors, so that they're much safer and efficient at the same time. So I've been mentioning that these 3 reactors, 3 Mile, Chernobyl, and Fukushima, belong to either generation 1 or generation 2 reactors, okay? Now these are generations, these are iterations that are done in industry every few years. First, it took maybe a decade or 2 decades to do the generations. Now the 3rd and 4th generations are already operative. In fact, the 3rd generations are being phased out, but they are already a quantum more safe and efficient than the first 2 generations that were the ones that melted down. We're into already in function 4th generation nuclear reactors, as you can see here, that is totally contained. There's not even water vapor, which these towers are very typical of 3rd generation reactors, and they're around and they're active. They're being phased out. What is this? Smoke?
Carbon
No. Water vapor. Water vapor.
So we cannot.
This would be, at least assuming that this is occurring in a civilized nation, all right, a developed nation of the world where there is regulation and control and EPA and all this, and even NGOs watching and all kinds of environmental groups monitoring this stuff, Earthwatch, you name it. This is water vapor. These are the cooling towers of the reactors where they run the water that is so hot that it steams up and it goes into the environment to cool out as clouds, essentially. These are artificial clouds that are being produced, totally inoffensive, okay? The problem is the spent rods, the nuclear rods that have been used, that are still nuclear active, okay? They're still radioactive. What to do them? Now they're stored, they're buried, etc. One creative idea is to bury these spent rods, nuclear rods, that have been used for their nuclear capacity to do the work to generate the electricity, but they can no longer be used by industry, either in third or fourth generation reactors, in third generation reactors. What to do with the spent rods, okay? They're being buried, they're being contained in lead and so forth until the radioactivity with the half-life thing decays over dozens or hundreds of years. One creative idea is to pump these spent rods down into old fraction holes that have yielded out their material already, have yielded out their natural gas and already old fraction holes, to bury these spent rods down there 1, 2, 3 miles deep down, where they will decay, and that would be totally safe for the environment. Because we go out with a Geiger counter right now into outside here, outside these walls, into the grass, and we'll get hits on a Geiger counter. We get radioactivity, all right? It will be a slow hit, click, 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 you know, but we get a background radioactivity that we're constantly exposed to all the time, right? In some areas, the Geiger counter goes higher just simply because there's more uranium, there's more radioactive material in the ground, in the mountains, in the soil. If you go to the Rockies, you get higher counts in general because there's more of these radioactive materials in the soil and in the mountains, all right? Just background, that's still background noise, radioactivity, and people have lived there for hundreds of years. And there's a background cancer rate also that may or may not be associated with that radioactivity, all right? But there's always a background cancer rate in any population. The issue is the spent rods. So a creative idea is to pump them back into these holes, old fraction holes, fracking holes, and seal them there and leave them there until they decay. They're done, all right? And there's the p-value of that radioactivity going through 3 miles of rock and bedrock and so forth is like, I'm going to guess, 0.0000001. All right, you can add maybe 5 or 10 zeros, I don't know, on the p-value to that one. Okay, so that's a very creative, good idea. Beyond that, the fourth generation, which are already in place and active, as you can see here, this is an actual photograph of a fourth generation reactor going on. There's nothing leaking out here. And even I understand that the spent rods are recycled even. So these are highly efficient, and there is practically no spent rods waste. All right, so these are highly efficient and also highly safe. The redundancy that is built in, they have much more redundancy built in of shutting down reactors way before the temperature gets anywhere near meltdown, okay? And so, and even generation 5 reactors are in the plans. Not yet fulfilled, not yet in construction, but you understand that the physics and the engineering that goes behind designing a nuclear reactor, right? A nuclear power plant is extensive. The engineering, the math, the physics that has to go into it, all right, including the chemistry. And so in the plants are already generation 5 reactors, which would be essentially extremely safe and extremely efficient. In other words, when we translate this existentially, nuclear energy is not going to go away. It's just too powerful to let it go. Certainly, it is being researched extensively in the military. And where there is spin-off for industry, well, then that particular nation already has a leg on the economy, has a leg up on the economy because they can get away from fossil fuels and into nuclear energy that will be safer and more efficient to produce and to use, right? Okay, but in the meantime, perception is so bad on nuclear energy that I read last year, essentially the Prime Minister of Germany, Merkel, buckled into social pressure, and they're dismantling their nuclear reactors, okay? Dismantling all the nuclear reactors, and what they do for energy, essentially, northern Germany has to go into wind, I believe, and southern Germany has to go into hydro, mostly hydroelectric, and then solar wherever they can get it. So those are the three main alternatives to nuclear and fossil fuel in Germany. But it was mostly because of political pressure, and that political pressure was mostly because of the public perception of the danger of reactors. And this one, it was Fukushima that did it for them, because they were very advanced in nuclear energy, of course, keeping the background of Nazi Germany in mind, right? That they were about to have the nuclear bomb also. That's why the Manhattan Project, it was so secret and so forth, because there was a race for nuclearity on both sides of the Atlantic. Well, the Allied forces versus the Nazi forces, okay? Anyway, nuclear today, controversial, but with enough technology, enough ethics, and enough willpower, it can be done, and it would be a very good transition until, because it is non-renewable, right? By principle, we use the nuclearity, we use the radioactivity, so it's non-renewable, but it would be a good transition into non-renewables. Okay, let's look at an overall picture here as we shift into renewables. Historically, since the birth of the nation, we're looking at the USA, about 230, 250 years more or less, a little over 200 years. Up until the 1850s, the bulk of the energy source in the United States was burning wood. Burning wood. I mean, think of the cottage environment, the log cabin and the log fire, right? And the fire that, the log cabin that catches on fire. So it was wood all over the place. Burning wood was a source of heating water and cooling and sterilizing water for drinking and everything else. Then in the 1850s, coal is discovered as and used as a source of energy, mostly, and you see that it correlates to the Industrial Revolution, mostly for burning coal to generate heat, to run the what engine? The steam engine, exactly, the steam engine. So you see how this curve takes off. In the second half of the 19th century, you understand the 19th century is the 1800s, it's always like that, right? The century is one number above the hundreds. So the 19th century is the 1800s. Okay, so the second half of the 19th century, coal takes off, huge. Then at some point, also petroleum begins to be used very slightly, and also natural gas begins to be used for the steam engine mostly, but also combustion, because what do we get by the 1900s? We also get another creature for transportation, courtesy of Henry Ford and Associates. The car, or the piston engine, right? The piston engine, which is different from the steam engine. So the steam engine is used mostly to turn a turbine to generate electricity, whereas the piston engine is used mostly for transportation, but also to turn it's an alternative type of engine, right? It works by combustion, by burning, by controlling the burning reaction, and the explosion of that burning reaction is used, rapidly expanding gas is used for turning a piston. And that piston then translated into work by a torque, by an axis that can turn something. And that can also either generate electricity, but more significantly can move a machine, can move a car, a truck, can move an engine, can move a railroad, all right? And so petroleum takes off, and also natural gas for the various purposes, but being burnt for the engine purpose, right? So this is all engine driven. All right. Then what happens? In the 1900s, coal starts getting replaced by petroleum, basically, and petroleum reigns, but also natural gas keeps increasing, okay, to where by the second half of the 20th century, the second half of the 1900s, we have kind of 1/3 each. Globally, about 1/3 or maybe 50% petroleum, and then 25% gas and 25% coal, or less. But they are reigning supreme in the century we just left behind, especially in the second half. It's mostly coal, petroleum, and gas, which are non-renewable, right? Fossil fuels, the infamous fossil fuels, so CO2, greenhouse gas, etc. Therefore, the need for filters and all that, and regulation. And to bring it up to this century, okay, what is happening is that we see that at some point we cross the line into non-renewables, and little by little, renewable sources are replacing the non-renewable sources. In the meantime, in the 1970s, more or less, maybe in the 1960s, 1970s, nuclear, which is represented here with dark blue, nuclear starts growing, and the graph I showed you previously is the representation of nuclear here. Okay, but then it leveled off, and then it got the bad rap after Fukushima. Here's Fukushima down slope. And so, in the meantime, the other renewables are expanding slightly. Mostly hydroelectric. Now, if you follow hydroelectric, which is just turning a wheel by running water on a river typically, okay, has been there all along, but kind of stable. It started way back at the end of the 1800s. What is that wheel? That's just a mill. Think of a mill out in the countryside next to a river or a stream. It's turning a wheel, and that wheel has an axis that is grinding the wheat or whatever is used for work. Well, then eventually with industrialization, that wheel got more creative, and instead of turning a grinding thing, it started turning a turbine to generate electricity, for example, to use for some other kind of machinery. And then people got even more creative and started accumulating, walling in the river so that they would have a larger flow of water. And then we get dams, the dams and the hydroelectric dams, right? And so all that is happening here, to the point that I heard one time that the vast majority of rivers in the United States are all dammed by a dam, not that they're condemned or they're, okay? They are dammed, meaning that the water of this river is being contained at some point and is used either for irrigation and or hydroelectric by the dam itself, okay? All right, so there it is. Now, what we're gonna do is we're going to look at this little graph, and then we're gonna take a break once we go into the renewables, all right? So this little graph just kind of summarizes everything. we have the percentage of renewable versus non-renewable energy source that is used in the United States compared to the rest of the world. Okay, so this is what these, just look at the two blue graphs for now, the two pie charts. Here we have, this is the percentage of energy that is used either by the United States or by the rest of the world with regards to renewable and non-renewable energy, okay? So in the United States, 90% of the energy is being generated by non-renewable sources. Meaning, what are the non-renewable sources? Fossil fuels and nuclear. Of this 90%, the bulk of it is still fossil fuels and a little bit nuclear energy, okay? Like for example, here in Miami-Dade County, what do we have? The nuclear Turkey Point down by the Keys, which I think is being dismantled. I'm not sure. I heard something like that, but Turkey Point is a nuclear power plant that was feeding the grid or is feeding the grid of FPL for South Florida. Okay, 10% approximately are renewable energies, okay, renewable energy sources for the United States. For the rest, compared to the rest of the world, in the rest of the world, about 80% is non-renewable and a little over 20% is renewable. Therefore, we are using less renewable energy sources than the rest of the world by about half. Okay? And so we need to catch up there. And that's why when they point at the climate change and global warming and CO2 production and greenhouse gases, they're saying that, what? China, number 1, India, number 2, and possibly USA, number 3, on the biggest offenders. Because we're still using a lot of non-renewable energies, and of that, the bulk of it is still fossil fuels. It's because of the economy. It's a market economy. It's still the cheapest fuel. And even recently, there has been discovered one of the largest yacimientos, one of the largest deposits of natural gas in the world in the United States, in the Midwest, down there. And that's why the fracking thing, okay? So industry is not gonna let it go. We need to find ways that the market can break even at least or go positive on it. But until that happens, it's still gonna be fossil fuels. So, sorry? It's India, yes, it's India. And in those two countries, China and India, sadly, it's mostly because of either lack of regulation or lack of implementation of the regulation, meaning corruption. Because they're competing at the world market with their products, and so it's more costly to put in the regulation, to put in the filters and all that and the monitoring. So they just, to the point that now Beijing and several other cities in China have this permanent cloud of smog, just like Mexico, for example, the Mexico City. And you see people in the news that walk around with a mask. The standard is the mask because of the air is yellow, okay? And in India also, so it's happening. Part of India is a mixed thing. Part of India is because it's a very large subcontinent, which has maybe 1/5 or 1/6 of the world's population, and a lot of it is in poverty, and they do a lot of burning still in primitive cooking, and so that is also generating CO2, right? Whereas China has gone highly industrialized. So for different reasons, but the net result is the CO2 pump. Well, we saw the annual budget, that 9 gigatons comes from somewhere. Okay, this is going to take too long, too much detail, so I'm just going to skip it. It's just the breakdown of the offensive gases, of the greenhouse gases by percentage. we're going to move on. What I'm going to do now, after the break, is look at the positive stuff, the clean stuff, all right, the renewable energy sources, which are these here. And I also had listed them at the beginning of the lecture: hydroelectric, biofuels, biomass, wind, biomass waste, solar, and geothermal. And I just listed here, they're ranked by percentage use, right? How they feed into that 10% of production of energy in the United States. So that's going to be the next slide, beginning with hydropower. So we're going to stop here. Any questions or comments before we take a well-deserved break? No? Okay, good. So we're going to go into break. If we can make it kind of short, it's already 11:30. We have maybe a little less than an hour to go. Okay, so pause recording. Resume recording. So now what we're going to do is we're going to look at the renewable sources, all right? Mostly here in the United States. This applies across the world. The biggest one, the numbers do correspond to the United States, the percentages, which is the percentage of this source for a total of 100% renewable, all right? Which, like we know, is only 10% of the pie of producing, of the pie chart, producing energy in the United States today. So the biggest one is hydropower, hydroelectric. Example of a dam here, okay? And as the water flows through that dam, it moves a turbine, and by moving that turbine, it generates electricity. So this is like a liquid alternative to the steam engine, right? If you want to think about it in functional, in physical terms, the liquid water running down and turning the turbine is the equivalent, the liquid equivalent of a steam engine. Okay, moving on. This one is more recent and it's become more prevalent, which is to get biofuels from organic material, mostly corn, cereals in general, but mostly corn. And it's a little controversial because it's also shifting the agricultural habits of the nation. This is what is known as a combine, all right? And a combine does, on the front end, it's picking the corn right through the plantation or the field of corn, processes it somewhere behind the cabin here, and pumps out a corn pulp, including the grain, which is, this will be very rich in grain. I don't know if it actually filters out the husk already, or this is a mix, but then this other machinery will eventually produce the grain. Okay, the grain is grounded and fed into a mashing machine. Eventually, that pulp is put into a fermentation chamber, and the fermentation will then produce alcohol or some derivative of an organic compound that is combustible, that has to be distilled into ethanol, which is a typical alcohol. It's an alcohol that is mixed with gasoline. And now you see the pumps, the gasoline stations mentioning 5% ethanol, 10% ethanol, right? This is the guy. And it's coming mostly from corn. And so what's happening is that farmers now, these combines, and I've heard that these combines, for example, they will start early in the morning. As soon as the sun rises, this fellow will get into this cabin, which is fully equipped, of course, with air conditioning, or heater, depending on what he needs or she needs out there. Typically air conditioning, I guess, in the crop season, it's typically in the summers, right? And what happens is he or she will spend the whole day there. So they'll take their lunch with them. They may even have a bathroom somewhere, I don't know, but they spend the whole day inside the machine as it goes through the field, all right? And it's highly automated and mechanized, as you can see. But what's happening is at the end of the day that farmers in the Midwest, particularly, which is the breadbasket of the US, the grain fields of the US, they're getting more money for their corn to be turned into ethanol than to be used as corn feed, either for feeding humans or for feeding cattle. And so it's shifting the industry. And what happens is then that has an impact on the price of corn, not only for humans, but corn feed for cattle, which is, my understanding is still a large amount of the feed for cattle is from corn. And so that corn feed is becoming more expensive, which that farmer, then that cattle rancher is going to pass on that expense to the consumer one way or another, making meat more expensive. Or putting some cattle businesses out of business because they cannot afford the feed, okay? So this is changing the landscape. This innovation is changing the industry also at the front end of things. But anyway, it's there, and while there is a profit, it's not gonna go away. We can see an increase. The positive side of this is that one way or another, this is a renewable resource, right? But there has to be other elements taken into account. For example, crop rotation, so that the soil is not leached out of corn nutrients all the time, year after year. They have to rotate crops. Maybe one year corn, the other year soybean, whatever. They have to rotate the crops so that the soil is not leached of particular minerals and then rendered useless. Because then that's worse, right? So crop rotation has to be built into the system. All that is very studied today with what is known as tertiary or quaternary agriculture. Primary agriculture is just letting the rain fall and gathering whatever grows from the rainfall, okay? That's primary. The secondary agriculture would be to make some channels to channel the water and begin to do a water management system on the crops. Tertiary is to introduce more technology into it, maybe some gathering technology for gathering the product and so forth. So the more technology gets involved, the higher the yield, more efficient. And those are iterations, just like we saw generations of nuclear reactors, there are also generations of agriculture. To the more industrialized nations, of course, have higher levels of agriculture that are much more efficient and hopefully environmentally friendly and so forth. This is another source that is fairly high. Forgot to put the percentage. No, here it is, 21%. It's interesting, almost from the renewable resources, just look at the numbers for a moment. For the renewable resources, we're saying that biofuels, in other words, basically the bulk of it is corn, is about 1/4 of the renewable resource in the United States today, okay? Mostly because of that ethanol biofuel. And then another 20% or 1/5 of it comes from wood chips. And this is what happens. The wood, which is waste ground up. Remember when we looked at recyclables? Wood is one of those categories, right? By wood, I mean also old furniture, wood chip that is used to build furniture. This, on the inside of these desks, I bet you anything, it's wood chip or wood fiber mixed in with collagen protein that comes from the hooves and the horns of animals, which is a paste, and it's built in, and it makes this stuff. That's why when this gets wet, it expands and it ruins, right? The cheap furniture that is made up of wood fiber. Well, all that eventually breaks, and that can be recycled by the good old burning of the wood, generating steam that will turn the turbine. So at the core of this one, we're back to the steam engine running a generator for electricity. Okay. Of course, there are two products coming out of this. One is carbon ash, which can be mixed into soil and put into landfills and so forth. That can be recycled because this is basically, as long as it remains solid, that ash is sunk carbon, right? And the carbon sinking, as long as it remains solid and can be mixed back into the earth. But the other one, of course, that is not shown here or just by the stack is the CO2 that would have to be filtered with the active charcoal and all that, right? But anyway, wood chip is still about 1/5 of the renewable energy. Is renewable in the sense that the wood is either waste wood or strands of forest that is grown specifically for this purpose. We can think of Christmas trees, et cetera, right?
Yeah.
It's part of the industry, yeah. Okay. Then another about 1/5, 19%, just under 1/5, is wind. And there are two basic types of turbines. Now we're back to the turbine in the sense that we need something moving to generate. We need a rotor and a stator to generate electricity. Okay, and so the turbines in this case are wind turbines, so there's no steam as such. This is the analogous, if you will, of the steam engine. It's a wind turbine. And the two basic models that have been developed commercially is this one with the three spokes that we see in photographs all over the place, including this one here. Typically along the shore where you have that strong wind, driving wind, all right, they only need to flap very slowly and they generate tremendous amount of energy of electricity in the turbine inside. You can see the scale of size. At a distance, they just look like little windmills, but they are huge. As you can see, these are actual trucks here on the road, all right? The other variant is this one, more like a helix that also turns. It's not as prevalent as this one, but I think they have slightly different properties on catching the wind. This one is available when wind is very variable. You don't know where the wind is coming from. Either way, because these blades are turned at an angle, wherever the wind comes from, it will turn it. Whereas this other type of blade is used for when there's a prevailing wind, and you can see that they're all oriented more or less in the same direction. Okay, so just trying to profit from the different types or the different sources of wind and so forth. But these are commercial, and that's renewable, of course, wind. Some downside of it, some people claim they're unsightly, and they can be, unless they're arranged in some kind of a pattern that is a little more sightly, artistically. But they can be unsightly, especially on a natural contour of a mountain range or something like that. Sometimes they're put in an area where they're hidden from view, at least from the road. You cannot really see them, but they're embedded in there somewhere. And the other downside is that they tend to kill birds. Birds crash into these things periodically, and some will die. Some will survive, but it does kill some birds. Not that much. So one thing to avoid would be migration routes and things like that, right? All right, moving forward, biomass. Now it drops down to 5%. The next ones are going to be 5% or less. So you can see that there's a tailing end here. There's a skewed, there's a skewness. Tailing down, all right, to 5% or less of renewables, of the 100% renewable, because we already had 1/4 from the hydro, another 20% from the turbine, and another 20 from the 1/5 from the biofuels. So that's 45, 65. We only have about 35%, let me see, 2020 is 40, and 25 is 65. So we're going to have about 35% to play with. All right, so 5% of that from burning trash. Burning trash, okay? And so a lot of the trash, just overall daily household and industry trash, commercial trash, office buildings, you name it, a lot of that material is combustible, right? It's combustible. There's a lot of plastics in there, a lot of wood in there, including paper, which is a wood product. So that gets dumped into a storage area, very smelly storage area, that then gets put into a combustion chamber. That combustion chamber is going to generate steam that will drive the good old steam engine turbine to generate electricity. It's also going to generate ash that can be taken to landfills, because as long as it's solid, remember, that is carbon that essentially is sunk. It's carbon that was not burnt enough. You know, maybe part of that ash could be also recycled because the burning was not thorough enough. Because basically this is kind of ground up coal, if you want to look at it that way. But also there is powdery ash that will be taken to landfills then, and that will percolate with the water. It's just carbon that sinks, especially with rainwater, right? The other nasty part is the fumes of the burning, and that's going to be mostly what gas? The fumes. Mostly CO2, right? CO2, but maybe some nitrous oxide, maybe some methane also, some organic gases that escape. That has to be filtered. So this whole back end of the industry of burning trash, this back end is filtering, cleaning. This is the environmental control here, so that whatever comes out eventually should be water vapor. Okay. But burning trash, and it's still happening, even in the cities. There's some stations of burning trash in the middle of the county of the city of Miami. The stations that are all self-contained in the middle of the city, and they do this kind of work. Of course, this is all sealed in concrete, and what comes in is trash. What comes out is ash, clean vapor, and electricity. Another 5% from solar. Now, solar is known mostly by the cells, which are known as photovoltaic cells, all right? Photovoltaic cells. And photovoltaic cells have a characteristic, and mostly they're made out of silica crystals. And what the silica does, it transforms, there's an energy transformation from light energy to electric energy, okay? Plus heat. There's always some energy loss when there's an energy transformation in nature. And that energy loss is heat that dissipates out into the environment, and from the environment to the atmosphere, and from the atmosphere out into the universe. So they're not 100% efficient because of the energy loss through heat, through entropy. But the transformation that does occur from light to electricity, then that electricity can be harnessed, right, into the grid, into the electrical grid. So here we have two examples. One example is the large commercial farms, solar panel farms, like you see here. Okay. I was driving down Chrome Avenue. You know Chrome Avenue, if you go west on the county, on Dade County, eventually you hit Chrome Avenue, which goes vertical straight down into Homestead, way down, okay? And is vertical. Chrome Avenue used to be the limit between civilization and no civilization. In other words, we humans were supposed to stay east of Chrome into urbanicity, mostly residential, but also some commercial. Now it's spilled over on the west side of Chrome, because what's on the west side of Chrome? The Everglades, which happens to be a national park. All right, but now there's spillover. Getting sidetracked. Anyway, not going to get that sidetracked. We're going to resist the temptation, but you can look it up later if you want. You can see where Chrome Avenue is on the map. Now we've spilled over, we humans have spilled over to the west of Chrome, and it started like farms, large acreage, 5, 10 acre farms out there for agriculture. But little by little, invariably, we go from natural setting to agriculture, from agriculture to urbanicity, either houses or parking lots or buildings, all right? And so that is encroaching on habitats, natural environment. Anyway, I was just driving south on Chrome to Homestead and look to the right, which is west, going south, and I see this solar panel farm out there, hadn't seen before, all right? Looked very similar to this, and did not inquire about it anyway, but most likely it's from FPL, and it's localized in the area. It's near, down by Kendall, West Kendall, and it's near, Kendall Drive out west, eventually where you hit Chrome Avenue and then go south, you'll see a solar panel farm that is, look pretty large, similar to this. It can also be used in residential at home, all right? So solar panels, we have a little solar panel station here, experimental station here at St. Thomas University, near the organic garden and our natural forest of slash pine, right, that you see coming in. But also, some people are getting creative. I think it's Elon Musk, who is the one who invented the Tesla and all that. He also has a SpaceX, he's going into space research or space commercial traveling and so forth. He invented these tiles that are photocells. They're photocells, but they're also tiles for the home. So it's is less unsightly, because solar panels as such, we put solar panels on the roof of the house. Yeah, but it doesn't look too pretty. And some municipalities forbid it, right? They don't allow it because it's unsightly, perhaps, to them. But this house, for example, this is a design of a futuristic house where it has solar panels, but the panels are integrated into the actual building, and they're tiles, which are photocells. But the car is also would be an electric car, and the pavement here, the driveway would also be panels and so forth. So and the house itself would heat and cool by convection currents, and there will be the southern exposure, or the exposure to the sun would be in the winter, and the exposure to the shade would be in the summer, and so forth. The house is designed ergonomically to use the environment. But the big issue here was the solar roof, okay? Generating electricity for the house. Difference is this other type of solar farm, and these, even though they look blue, these are not solar panels. These are solar mirrors. And these mirrors, you see that they are in a circular shape, in contrast to a farm, which is typically oriented in a parallel shape, okay? These mirrors, the solar mirrors, are in a circular fashion and angled all to reflect the sunlight onto this bulb on top here. And this bulb is beyond red hot. This bulb is white hot. White hot, right? And they're called concentrated solar power, or CSP. I think FPL actually has an experimental station like this in Central Florida somewhere. That's what I've heard. But this is what it does. So again, not photovoltaic, not converting light to electricity, but converting light to heat. Now, a lot of this heat is lost. Of course, it's white hot, so it's dissipating, it's glowing like a light bulb, which, by the way, was this light bulb glowing at night? Question. Well, we see this white hot bulb, which is huge. I mean, look at the scale. These are trucks down here. right? Look at the scale of this thing. This is a humongous light bulb way up in the air there on top of this tower that is glowing white hot. Okay, so it's very hot. Will this glow at night? No, because there's no sunlight. So it's cold at night. But during the day, it's very hot, and that's why it has to be so high, because it's radiating heat volumetrically 360 degrees around. And that's why it has to be so hot, because if it's closer, it's going to melt everything around it. So it's so hot, and the bulk of the dissipation is going up into the atmosphere. So what is this heat doing? This heat, some of it, a small amount of it, is being trapped into conductors, metal conductors, that is brought down into these chambers. And in these chambers, that heat that has been trapped into the conductor is now turned into steam to run the steam engine. All right, so the heat is used to run a steam engine, and the steam engine is the one that generates the electricity. So we can say that functionally, this bulb is replacing the wood burning, but it's generating heat to run the steam engine. And so sunlight is being used, bypassing the whole organic process of growing the forest, cutting the forest, burning the forest, and getting the steam, getting the heat out of it. All right? So it's a very interesting, innovative way. But so far, it's only about, together combined with the solar panel, with the photovoltaic, together, both, it's 5%. And of these two systems, the bulk of it is still photovoltaic because it's just more commercialized. This one, of course, there's a risk factor, and the construction itself is expensive, and it's dangerous because this thing is white hot and so forth. So it requires much more regulation, right? And therefore expensive. Moving forward, we're down to 2% now. Trying to get to some of the heat again to run the turbine. So good old heat comes back to steam water, right? To run the steam engine, the turbine. How about the hot soil or the hot earth? Because remember, the core is red hot, and it's in fact the core, the very core is white hot, can get to it, but the mantle is very hot, and it has heat conduction that transmits all the way to the crust. And so the crust, the bottom part of the crust, is also extremely hot. If we can tap down there into some of that source of heat, mainly by hot water, the hot water springs, then that hot water could be, the steam could be used to generate electricity through turbines. Then some of that hot water would have to be cooled eventually and pumped back into the aquifer, whatever it is. But these are hot springs that are throughout the US, not that many. Yellowstone, for example, has some, but that's a national park, so it has to be left alone. These are all calderas. Caldera is a spent volcanic crater, right? But it's in use, and it's generating about 2% of the renewable energy in the United States. It's known as geothermal. Okay? So trying to tap into the heat. Imagine this heat essentially is immense, the amount of heat that is trapped at the core of the earth, right? And even at the mantle of the earth. So getting creative there. All right, rounding it up. I want to see. Oh yeah, because these are the main sources. Let me do this for a moment. I may. Right. So we have, yeah. So we have solar, wind, hydroelectric, geothermal, biomass, biofuels, and now sources are the more creative ones. There are variations on the theme. We'll get to first. We'll get to after the graph, but I just want to round it up here with another graph. What do we have? Power sources in the United States since the 1950s forward. when all the graphs, all the different sources begin to differentiate at the beginning of the 1900s. That's going to coincide with the Industrial Revolution, right? Driving massive need of energy source to drive the industry and increase transportation and well-being at home, including electricity, so on and so forth. Okay, so the usual suspects are here. The first four are non-renewable, right? You can recognize coal, petroleum, and natural gas, and then nuclear. Renewable is this fifth trend. So let's look at the non-renewable first. And of the non-renewable, the fossil fuels, again, coal, petroleum, and natural gas. Blue is coal, which this correlates to that other chart that I showed you. Basically, coal has been the driver of mass production of energy in the United States in the 20th century. You can see the rise until the turn of the century of the 2000s, where coal is dropping rather fast, okay, which in principle is a good thing because it's one of the major producers of CO2. And so that's dropping, but it's still the cheapest one by the money, by the pound, if you will. Then, secondly, is natural gas, which actually has increased. You follow natural gas was keeping a low profile through the 20th century until the end of the 20th century. The last decade, it started taking off and is still on the rise. And again, this may correlate with the resources that have been found of natural gas in the United States, one of the largest deposits. So industry is not going to let that go if it represents cheap energy source. So it's there. Then look at petroleum. How interesting. Petroleum was low, certainly much lower than coal and natural gas. But then in the 70s, I don't know if you remember, but in the 70s, gasoline was very cheap. It was 25, 30 cents a gallon. Yeah, amazing. Because I was alive in the 70s. I was a young kid studying college here in Miami, went to Miami-Dade first, into FIU, and I had a Falcon, a Ford Falcon from the 1960s that cost me $100. It was a junk car. It had natural air conditioning, roll down the window, even had a hole in the floor. It used as a natural brake if I put my foot through it. But it got me from my little apartment to MDC for 2 years, and then it conked out, and then I bought a nice splurge, and I bought another junk car for $200. That took me to FIU for the next 2 years. And I remember paying 25, 30 cents to a gallon because gasoline was being subsidized by the government. Okay, this is before it was deregulated. And I tell you, I was in my late teens. I was 18, 20 years old, 21, 20 years old. When it went from 30 cents to 50 cents a gallon, I said, I will not pay it. I put my foot down and says, no, this is too much. It almost doubled because it was deregulated. I said, no, that's too much for gasoline. I'm not going to pay for it until it comes down again. Well, to this day, right? Quickly, within a day or two, I had to give up on that promise and start paying again because it has never been 30 cents again. All right, it was deregulated and it started floating and everything else. So, but that's precisely here. That is that hump right here. And so the consumption went down when the price went up, but it stayed. And now it's really very low. In the 2000s, it's interesting that gasoline as a whole, or petroleum as a whole, is producing this little of the national consumption of power in the US. Translated into kilowatts, of course, translated into electricity. So this, obviously, what is excluded from here is transportation. Because transportation is not using electricity, right? It's running the piston motor. Okay, but that's the fossil fuels. Then nuclear. Again, in the 70s, as we spoke, the research and the development, and it went into industry and commercialized the first and second generation reactors, up to the third generation reactors now, is slowly, but it levels off, right? Bad PR. What happens here in the 90s, well, in the 70s, we had 3 Mile Island. This is 3 Mile Island, probably. Okay, the little dip there. Then after the Cold War, this may be Chernobyl, the dip. And anyway, Fukushima also influenced the leveling off. But it's there now. It's the bad rep before they get those generation 4 and 5 reactors out, which are big investments. I mean, typically those things will cost billions of dollars to build. Finally, renewables, the green. Okay, the green is interesting because it's been there mostly what? The green has been mostly back even in the 50s, the 19th century, the first half of the 19th century into here, 1900s, sorry, into this part, mostly hydroelectric, right? The renewable hydroelectric. Again, the windmill, the mill, the grinding mill on the river or the stream. Then it got commercialized, the dams and so forth. And then other renewables kicked in, the hydro, the solar, the wind, solar continues. And it's the graph is more up and down, has more fluctuation, more variation. But this development, since the turn of the century, since the millennium, what do we see here? We see an uptick that seems to be exponential, which is very exciting. From the curves, the only behavior that it has a positive exponential is renewable. That's exciting, it's promising. Positive exponential means that it's a geometric progression as opposed to linear. Contrasted to coal, for example, it seems to be, if we average this out, this could be smoothed into a negative exponential, all right? Maybe gas, maybe a long-term exponential, it's hard to tell. But this one, at least at the beginning, the early on, this could be known as the lag phase and the log phase of an exponential curve, of the sigmoid curve, all right? So for renewables, that's very promising, right? Okay. Moving forward, some creativity. This is a little more on the lighter side, but creative ideas. Here is one that is using wave power. Waves are constant. So we're looking at nature, what's out there that can be used, that has some kind of motion. Motion can be translated into doing work, all right? And so this worm, this artificial worm, just lies there on top of the ocean, on the surface of the ocean, and by the wave action, the actual wave of the ocean, it generates a wave motion on the worm, and as that worm oscillates, it generates this oscillation that will generate electricity somehow. Okay, so basically inside there are going to be some sophisticated type of friction that will generate electricity. Similar to this other one, these two things, these are actual photographs, so these things exist, right? These two contraptions move up and down on the wave motion on the shore, which is translated into an up and down waving motion, and that in itself, can generate electricity somehow. Okay, so these are examples of creativity. Of course, the electric car. Proud owner of one of these. That's the Leaf, Nissan Leaf, which is actually an old model like mine. It's 2015. That's about 90 miles on the gallon, 90 miles on the charge. But now the standard on the electric cars is around 200 miles on the charge. all right? So more than twice the range. So the technology is improving. Transition on light bulbs, for example, to save electricity from the incandescent, the standard incandescent bulb. This gets white hot precisely. We remember that it gets white hot when we try to change one of these things. We have to let it cool down before it burns your fingertips, right? Or use a handkerchief or something. So this went from the incandescent to the fluorescent, which is lighting up a gas inside, making that gas fluoresce. And then that emission of photons, which is essentially the photons, right? That give light, that are light. So more efficient, but they're more costly also, but they last longer. So it's a market thing. Finally, the latest is the LEDs, right? Which stands for light emitting diode. So this is a very different technology to generate essentially the same, which is a photon. The photon is a light beam that allows us to see. And that's what the light bulb should do, allow us to see, right? When there is darkness. So a diode is simply a chemical that gets excited and emits a photon or millions of photons. And so these diodes are light emitting diode, and to stimulate this diode to release a photon is very efficient because it takes a very little amount of energy, right? It's a transfer of energy at the chemical level. And so with very little wattage, many more photons can be emitted. And so the industry is going to put a price on that advantage so that they cost more, but they last longer. Okay. And here, the important thing about this comparison, this table, is on the lumens. So the lumen is the equalizer, if you will. Lumens is just a light measure of how much luminosity a bulb has. When you look at the lumens, it has about the same luminosity in the 800s. It's in the same order of magnitudes. So we can say that it's fairly equivalent. In other words, if we were looking at a light bulb, our eye could not distinguish between 800 and 840 lumens, okay? So this is essentially, let's call it bright enough to see. This is a 60-watt bulb. I don't know how recent you are, but I'm very familiar with a 60-watt bulb. It's kind of, it's an okay light for a small room, but if the room gets larger, 60 watt is kind of low. You know, you want 75 or 100 watts, right? In the old bulbs. All right. So that's what it would be. It would be equivalent to around 800 lumens, 840, 825, 800. It's about the same for the eye bulb. So this is the equalizer on the table. Now, if we go up on the table, we see that it takes 6 times more wattage to get essentially the same amount of lumens from an incandescent to an LED. So an LED, we can say that as far as wattage is concerned, is 6 times more efficient to produce essentially the same amount of light. Get it? Okay. Now, on the bottom side of the equalizer, the duration of the creature. An average 60-watt light bulb, put it to just under a year, round it off to a year. Fluorescent, 10 times longer, will last 10 times longer, all right? But the LED will last you 20 times longer. Okay? I mean, we sold the house before the 22 years go by with the LEDs. We got to be careful, you know, buying LEDs for the next generation. But they'll last you essentially, you know, in fact, one human generation is considered 20 years, more or less. So you're buying LEDs for the next generation, essentially. You can take it to retirement to try to put it functionally, right? I always try to think functionally. Okay, then cost. This is, so the straight up cost for a 60 watt, $2, straight across to $12, so it's 6 times more expensive. That's equivalent, right? Because it's 6 times less efficient. So these two numbers are equivalent, the top and the bottom. The 60-watt bulb, look at how the equivalency is done in the market. The 60-watt bulb is, let's put it this way, sorry. The LED bulb is 6 times more efficient, right, in wattage? It's 6 times more efficient than in wattage than the incandescent, but it's 6 times more expensive. So 2 times 6 is 12. So what we're paying here is wattage per wattage. We're paying for the wattage. So the LED is more expensive, but it will last you 20 times longer. So per year, you amortize it, and it comes out to about 1/6, yeah. So the prices have to equal. So per year on an annual prorating, this one is $7. This is almost $2, $1.50. So you see the 1/6 proportion there roughly. Anyway, it depends. If you're gonna stick around with the bulb, go LED. And they generate much less heat. That's the other thing. This one is generating more heat. So side advantage, indirect advantage of LED, your AC bill should be a little less because you're not producing white heat in the house. Right? Already fluorescent is cold, what they call cold light. They still get a little warm, the fluorescent, but not nearly as hot as the incandescent. So interesting table, and definitely LED overall takes the day. Innovative has been found. Look at this train. It's a magnetic rail. You look under the train, okay, it's empty.
Yeah.
Exactly, look at under the train. So these are magnets. These are magnetos or magnets generated. It's a pulsating magnetic current that moves along the rail, okay? And the magnetic current moves ahead of the train, and then the other magnets, the other pole is on the side of the train here, kind of bracketing it. And so this, I guess, I don't know how it works out. This probably has a fixed polarity, but the rail is moving the opposite pole in a pulse ahead of the train. And so it's constantly pulling on the train. It's pulling on the train, okay? And the physics is all worked out, the electromagnetic forces, so that the net result is that the train moves forward much faster because it has no friction, no friction. So aside the fact that there's no heat generated, which is the least concern, the friction, the energy loss in friction is bypassed. So this is the highly efficient, and those are high-speed trains, okay? All right. There are some other videos here that generating electricity from plants and also obtaining biofuel, actual biofuel mass from algae. Don't have the time because it's getting late, but take a look at the videos when you review the PowerPoint, all right? They're short videos, 2, 3, 5-minute videos. You can take a look. In construction, some innovation. Again, aside from the solar panels, these are water heater panels, water heater. Okay. The water is put through these tubes that is heated up just by sunlight, and then that hot water is stored. So this is the storage of the hot water, which is used when people use hot water inside the house. So it's a passive way of heating water, just exposure to sunlight. Also, the actual design of the house, so that there would be passive cooling or passive heating, depending if the house is in a mostly hot environment or a mostly cold environment, all right? So depending on where it is on the temperate zone, if it's above the temperate zone or below the temperate zone, if it's below the temperate zone, you want to have passive cooling, which means that on the sunny side of the house, you're going to have mostly shade, including large trees that would give shade to the house on the sunny side of the house, okay? And on the shady side of the house, you're going to have some ventilation up this area up here. It's called clear story. Clear stories that will open up, panels that will open so that they will create a breeze from the shady side, bringing in cool air and circulating it through the house, all right? Because hot air rises and will cool and will come out through the clear story on the high part of the house. So this is a passive way of cooling a house in closer to in equatorial areas. In northern areas above the temperate zone, what we want to do is retain the heat. And so we would put the exposure side to the sunny side, the exposed side of the house. We would design it, basically turn the house around. And you have now the clear story will be facing the sunny side so that sunlight actually comes in, hits the wall, and generates heat. That heat is trapped inside, creating essentially like a little greenhouse effect inside the house, because the light will come in through the glass, hit the wall, and the wall, some of that light will transform into heat, but the heat will be trapped because of the glass, right? So this red arrow is when that glass is open. But if the glass is closed, then that heat is trapped into the house. It can also be used for heating panels here, and that hot water could be circulated into the house. So this hot water could be used for the radiator instead of, or including the shower, but also the radiator, which will radiate heat inside the house and so forth. Put the windows on the sunny side to allow all that to heat up the house on that side. Another one that is called the Titan is a water heater that is only per use, all right? So the classical tank in houses is this water tank that keeps the water hot all the time. But it's that hot water is only used part of the time, a little bit, typically in the evening or in the early morning when people shower and when people are at home and are using hot water. But the rest of the day, that tank is being heated uselessly because it's not being used, all right, which is the bulk of the day and the bulk of the night also, because in the middle of the night, the hot water is still hot and no one's using it. The alternative is this thing called a Titan, which is through electrical current. It heats up the water instantly, almost instantly. As the water flows through the coil, that coil gets so hot and so localized and intense that it heats the water as it runs through to a particular temperature that is comfortable for the body. So it's much more efficient. Of course, a little more costly front-end investment, but in the end of the day, what this does, it saves a lot of electricity. So this amortizes maybe in a year or two of electricity, of the extra electricity that is paid with the traditional hot water tank, okay? They're called Titans, and they are tankless because the water is just, as it circulates through the coils in here, it gets heated up almost instantly. They require a dedicated line of electricity because it's a little higher. I think it's a 30-watt line or something like that. Anyway, creative ideas for the home. If we go commercial, there's this LEED, the LEED buildings, okay, and LEED is an acronym for Leadership in Energy and Environmental Design. You can look at it in more detail, but it's essentially a certification. It's a LEED certification that is very prestigious, and it is supposed to be environmentally friendly, all right? Not supposed to, it is environmentally friendly. So it's a cluster of things that the building has to qualify for. And here's a list of the requirements of the categories, beginning with the design and the construction of the outside of the building itself. Then the interior also has to be what is known as a green interior, meaning that it's environmentally friendly, more effective use of the air conditioning, et cetera, on the inside. Then the operations and the maintenance also, these buildings are supposed to be like low maintenance, so they're more efficient that way. They also look at the fabric, what is known as the fabric of the construction, meaning where the building exists, actually in the neighborhood, how it impacts the neighborhood, the surrounding. And finally, also, so all these are at the commercial level, but also it can be taken to the home level. And here's an example of a home that is green, that is LEED certified, all right? And there are different levels of certification. You can start with the basic certification, which is up to 50 points, anywhere from 40 to 50 points. So it's a cluster. One accumulates points by the different aspects of the building, of the design, how environmentally friendly it is, all right? So maybe, I don't know, give you an example. If it's passive heating, if it has solar panels, maybe it gets 5 points. If it has a Titan, it gets another 3 points. If they're using photocells and electric cars, they'll get another 15, 20 points to see how it works. And they accumulate points. Basic certification, then it goes to silver, the next 10 points, and then 10 more points. 20 more points take it to gold. And finally, above 80 points is the platinum standard, which is the highest standard in the industry right now. LEED Platinum also has certain advantages. You get tax breaks. This is at the commercial side. You get tax breaks, you get publicity. You're really at the forefront of the industry and the building industry to produce environmentally friendly structures. They have a minimal footprint on the environment and so on and so forth. These are a couple of examples. These are platinum certified, Washington, DC, a commercial building that typically has a mixture of office and living spaces, condos. This one is the tallest building, LEED building in the world. It's in Taiwan, and it is platinum certified. Okay, so this is the actual leader in the industry right now for environmentally friendly buildings. I don't know how much it costs, probably a lot. It also goes into commercial industry. This is a food packing commercial structure in Ohio that is also LEED certified. And also at the residential level, it can be taken down to the family neighborhood level. But these houses tend to be expensive. You see all the panels down here, up here. They're also going to collect water, and that water is going to be used in the house. The environment around it, the landscape is going to be, what is that called? Xeriscape landscape, which is the native natural stuff that grows there, so they don't need a sprinkling system or anything like that. Okay, very environmentally friendly. A couple of other innovations. Here we have, with regards to solar photovoltaic flight, the first flight that went around the world in stages, of course. It just happened a couple of years ago, 3 years ago. It's called the Solar Impulse 2. Here you can see a photograph of it as it is crossing over the that very famous bridge in LA. What's that called? The California, the Golden Gate. Golden Gate. There it is in red. It's not golden. It's red. Golden Gate Bridge is painted red. Okay, so it's going over that. This went around the world in several stages. The longest track was, of course, from the Pacific to, it was coming from Asia into America. And I think the stop was Hawaii, LA, or something like that. It was several days. It had to be airborne, of course, at night. So they need some storage of energy, because at night the photovoltaic cells are not working, right? The other one is the ISS, the International Space Station, that has been up since the late 90s. And this is an entire cluster of labs that is international, that I know several nations are participating, the US, Russia, several European nations. I think Japan is involved in it, maybe Australia and so forth. The largest nations in the world are involved in this ISS. And what you see hanging out here on sides are solar panels. You can see they're oriented at different angles to try to maximize their exposure to the sun. And this is what is powering this station, which I heard recently is now becoming obsolete, and it has outgrown or outlived its purpose. And within a few years, it may come crashing down to Earth. Of course, the bulk of it will be burning on the incoming, right? And it will just be just a flash in the sky. But it's amazing. This is the largest artificial structure that humanity has built, and it's floating in space. Okay, and they have, at this point, astronauts have lived here. Some have lived up to a year, maybe more, in here, okay, with flights back and forth. Part of it is military and part of it is commercial. But this is a very interesting, exciting thing that the human mind can do when it's creative. Finally, not to leave the Catholic Church out of all this and to reroute it to the bioethics thing. Just a couple of minutes. As recently as last year, Pope Francis had a two-day conference at the Vatican with major leaders. These are the CEOs of 40 gas and oil companies of the world. All right, and here they are all sitting, paying attention, including a few bishops and cardinals and other people in the background. But these are these 40 major leaders of Exxon, Eni, which is Italian, BP, British, Petroleum, Dutch. Norway is Equinor, Pemex is Petróleos Mexicanos. All right, so these are the major oil industries in the world. They're CEOs with salaries in the millions, right? Gathered, paying attention to Pope Francis' delivery. I invite you to be the core of a group of leaders who envision the global energy transition in a way that will take into account all the peoples of the earth, as well as future generations and all the species and ecosystems. Okay? It's just one excerpt from the document. It's a two-day conference. The first amazing thing is that they came by invitation of the Pope to gather, okay, and to dialogue about this and to see how we can make the industry, the oil and gas and petroleum industry, more eco-friendly. And they listened and they signed some kind of agreement. But they talk about the Memorandum of Understanding, right? The MOU, which is, in principle, they agree that they should do these things. They should try to be more eco-friendly and so forth. I'll send you the link to the document. It's only about 4 or 5 pages, but there was a document released on this, on the mutual agreement. So you can see that this man is moving forward very strongly, consistent with Laudato Si, which we saw in other courses here at the program. So bottom line, human creativity really has no bounds. You know, when we use it for the good, we can really survive as a species instead of destroying the environment and destroying ourselves in the process. Okay, thank you very much. You've been very kind and patient to endure all this. I'll send you the PowerPoint, I'll send you the lecture, and I'll also send the papal document there on these things, okay? Questions, comments? No? Monica, you okay? Okay.
Yes, thanks, Father.
Okay, so let me stop this and we'll see you next week. Thank you very much. Bye-bye.